May I have your attention, please? Starting at 1:30, the Yonsei Quantum Week 2025 International Conference will take place. If you have not yet taken your seat, please do so now. Thank you for your cooperation. Good afternoon, everyone. We will now begin the Yonsei Quantum Week 2025 International Conference. First, we will have the opening session by our Director General, Professor Jae-ho Jang. Please give a big round of applause.
Good afternoon. Yeah, it's gonna be a long day, but from morning to the evening, we are going to have a long journey. By the way, I think this is a quite historical and momentous time. So it is a great honor to welcome you all to this, sorry, the wrong one. So yeah, the inauguration of the Yonsei Quantum Complex and our accompanying international symposium, this one, and today marks not only the physical establishment of a pioneering research hub, but also the beginning of a new chapter in scientific discovery and transformative innovation. Quantum computing stands at the frontier of human knowledge, promising to revolutionize the fields from cryptography and artificial intelligence to drug discovery and sustainable and affordable healthcare. At Yonsei University, we recognize the profound impact that this technology will have on society, industry, and academia, and overall of human life. Our commitment to advancing quantum research is unwavering, and this complex is a testament to our dedication to fostering groundbreaking collaborations and transformative advancements. We are honored to be joined by leading experts and esteemed scholars and visionary pioneers in the field of quantum computing. Your presence here today reflects the shared enthusiasm and commitment that unite us in the grand pursuit. Through interdisciplinary commitment and cooperation with the strategic partnerships, we aspire to push the boundaries of knowledge and accelerate the realization of quantum-enabled solutions to some of the world's most pressing challenges. This symposium provides a unique platform for the exchange of ideas, fostering discussions that will shape the trajectory of quantum research. I encourage all of you to engage in meaningful dialogue, challenging existing paradigms, and inspire new pathways toward discovery. On behalf of Yonsei University, I extend my deepest gratitude to our distinguished speakers, dedicated researchers, and all those who have contributed to making this event possible. Your expertise and insights will undoubtedly drive the success of this endeavor and fortify our collective mission to lead the quantum revolution. Once again, welcome to the Yonsei University Quantum Complex, and may this gathering spark new collaborations, ignite innovative ideas, and pave the way for an era of quantum excellence. Thank you.
Next, we will proceed with International Conference Session 4 with Professor Jae-won Kim.
Hello, good afternoon. My name is Jae-won Kim. I'm the director of the Institute of Quantum Information Technology at Yonsei University. And I'm chairing this first session this afternoon. And okay, before going to do that, so I have a one-page manual how to read Korean characters. So if you are interested in learning how to read Korean characters, come to me after the session. One-page manual. You can learn it in 15 minutes. Okay, Yonsei University's mascot, do you know what that is? Eagle, yes, eagle. And in what it feels like an act of divine providence, Yonsei has acquired IBM's Eagle quantum processor, featuring 127 qubits. And we are living in the era of the second quantum revolution, where quantum information technology, especially quantum computing, is highly competitive. Progress in this field is being pursued along multiple directions. And you can read in recent newspapers. And scalability, increasing the number of qubits, and the quantum interconnects, and computational depth and coherence time. A key metric for evaluating these advancements is quantum volume, a measure that Dr. J. Gambetta has been working diligently to improve. Beyond quantum volume, Dr. Gambetta is also focused on achieving quantum utility, aiming to make quantum computing practically useful. Just as the semiconductor industry, followed by Moore's law, which predicts the number of transistors in a chip doubles roughly every 18 months. Quantum computing follows what we might call Gambetta's law. Do you know what that is? Where quantum volume has been doubling annually. I'm not sure whether this is a law or theorem or whatever. Dr. Gambetta earned his PhD from Griffith University in Australia under guidance of Howard Wiseman, and focusing on theoretical research, I guess. He then completed postdoctoral positions at Yale University and the Institute for Quantum Computing in Waterloo before joining IBM. In 2019, he became IBM's vice president of quantum computing. And he's working on many, many things for quantum computing. So I would like to give him a nickname. He is conducting an orchestration of quantum efforts. So he's a conductor. Again, he's a superconductor. And he's working on superconductor. And today he will speaking on the path to quantum advantage. Please join me welcoming Dr. J. Gambetta.
Oh yeah, I gotta pick it up, right? Does this one, am I using this one or this one? Okay, so thanks for the introduction. I'm not sure what to say. Yeah, I'll start with superconductor. I agree we're living in the second quantum revolution. And so why am I excited about the next few years? I'm gonna try to, in this short period of time, give you a sort of a summary of what I think can happen. Sorry. Okay, we're all here because we believe that quantum computing basically has some problems that will be easy on a quantum computer that will not be on a classical computer. Fundamentally, it changes what we mean by compute. Problems that most famous of them, factoring or even simulating chemical reactions, materials. There's many of the examples along this lines. But essentially, we know of many algorithms out there that if we can solve, once we get a quantum computer that's big enough, if we can solve them, we'll not be able to do them on it appears we will never be able to do them on a classical computer. So think of quantum computing as the only technology that breaks that. At IBM, we have a roadmap. I'm not going to go through the details of this roadmap too much other than say a couple of things. First, we're very proud of the fact that we've hit every milestone since we made this roadmap public. So in 2019 to 2024, I didn't update this roadmap. Yeah, sorry. To 2024, we've hit all the outcomes. And one thing I want to point out is we expect over the next few years to keep increasing how many gates can be done on our systems. And that's what I sort of show in the number up the top with 5,000 to 15,000. And then you see a big jump to 100 million with Starling and 1 billion with BlueJay. That is error correction kicking in. And so we're confident that we have a path towards error correction in the later part of this decade. But this talk I'm going to focus on what are we going to do in the near term. But before we go there, essentially in a quantum computer, you can think of the thing that executes on the quantum computer we call a quantum circuit. And there's two things that matter: how many qubits and how many gates can be done. And I've just taken a summary from references of various different papers here. And you see in these shaded regions numbers of where certain algorithms, whether it's in materials, chemistry, optimization, or crypto-relevant problems can be solved. So you see that's right out there at circuit sizes that are quite large. You see the shaded region we call pre-utility. What we mean by that, if it's smaller than that region, we can simulate it on a classical computer. So where are we? So a little bit of honesty, we're actually just crossing this region at the moment. We're just getting out of what we can simulate into a new region. As I said, we have a roadmap that with Starling and BlueJay, we definitely get ourselves to do these pen and paper type algorithms that many famous algorithm researchers have researched. One of the questions we're asking is, are there potential numerical method advantage algorithms in this white region where we can start to access now? And it's not completely out of the question, because there's papers like this paper by Sergey Bravi, where they show that they can actually show for what we call short depth circuits, there's actually a separation between what classical and quantum for what we call a shallow or short depth circuit. This was a game that they proved, but there's been various other papers that have come out on complexity of these circuits. So the thing I want to leave you with is, at the start, if the complexity of the circuits is hard, then these are the circuits that we expect to use as our resource as we search for quantum advantage. So number one first is you have to be able to execute quantum circuits. And then second, you need to have a set of quantum circuits that there doesn't appear to be some way of being able to solve them classically. And so you can start to take this, and I like this paper. I'll give you some examples before I go a little bit more. There's a paper out of the Riken team where they look at time dynamics of so on the top where you see the white lines, the black lines, white lines, black lines, it's like a striped material where either all the spins are down or the spins are up, and then they hit it with a dynamical equation. And if you're in certain one region, you find that the oscillations continue forever. If you're in a region beyond the parameter space, you find the oscillations decay exponentially. And then if you're in the critical region in the middle, you get this beating type pattern. They were able to run this type of circuit at 133 qubits with 15,000 gates, do like essentially 100 flock gate cycles, so many of those down there. And they are able to go to a regime where you can't do easy numerical simulations, but at the small cases of 28 qubits, they find that the smaller systems agree. So the conclusion of the paper is that this sort of many-body physics problem, they can start to look at interesting dynamics, okay? So that's one. A second is, what if you mix up how you look at algorithms? So I said at the first, you want to start by running some type of quantum circuit. Here, I just called it U. And now imagine I also know that I'm interested in a problem where I actually want to find the ground state, be it some chemistry problem, some material problem. So is it possible to run a quantum circuit and use the quantum computer as an input into a classical computer? So in this algorithm, what we imagine is we create some exotic quantum circuit. We then find a way that for that quantum circuit, we generate samples. Now those samples are finite in size, say M samples. So we can define a new effective Hamiltonian. And the key here is this new one is no longer exponential. So if it's no longer exponential, it can be diagonalized, and we can report some energy. And it turns out, this paper was prototyped with our colleagues at RICAN again. It turns out that we can actually start to do chemistry solutions that I would argue are comparable to the best classical methods. They're getting on the same sizes of DMRG type simulations. Cleveland Clinic, Lockheed, and ourselves have extended these type of methods to even further. So what this is suggesting is now we know there's something complexity hard about those circuits. Let's use them as an input into a larger algorithm, and then we're able to start to explore it. You can even go one further. And I think this is another beautiful example for those experts in the field that know of phase estimation. Now I'm going to imagine that I'm going to create subsamples of different evolutions of the time. So now my matrix is dm times dm, so it's not exponential, but now I create basically subsamples where I have the different time dynamics, and now I'm able to diagonalize this type of problem, and if I can diagonalize this type of problem, I can actually get some of the, I have less assumptions in the first state. I'm basically can say, if I've got enough DTs and I take it big enough, I actually know that I will converge to the right answer. So the teams were able to start to explore on that. So what this really starts to suggest in this near term is if you can start to mix classical and quantum computers together, we call it quantum-centric supercomputing, you are creating an architecture where we can start to explore, and we're getting comparable results to what we expect in classical computing. So one of the things we've said, I think many of people have heard me say that, is if together can we get quantum advantage in the next couple of years. So what I mean by that is get something that we run that is scientifically interesting, that is either cheaper, faster, or more cost-effective using quantum plus classical than classical alone. I do believe that this is going to be possible only if we start to really bring HPC. What I really mean by that is numerical experts in the classical world together with the quantum experts to start to do these interesting problems. So why are we getting confident that this will be possible? There's a few reasons. The first is everyone here, like Yonsei University, many of our partners, many people are coming with new ideas. I just put a couple of those algorithms at the start, but there are many more. And second, the hardware is actually getting pretty good. I'll give you this example. In 2023, so not too long ago, we set out to show that a noisy quantum computer can produce accurate expectation values on 127 qubits with 3,000 gates. That is outside what we call brute force, so that's outside where you can classically simulate it. and showed that it can get accurate results. And I want to show you a little example. Imagine I give you this toy problem. Each one of these black boxes are going to be a different experiment. They're going to be, I'm just going to tell you it's an experiment. That experiment happens to have two parameters, an angle and a quantity that is measured on a quantum computer Z. For the experts in the audience, this is just the spin of the 62th qubit in this. This is an Eagle processor as well. So actually an older version. The one in Yonsei is better than this one. Of this, we measure the 62 qubit spin as a function of this angle. So the first thing you notice for all these black boxes, none of these lines are actually the same. They're all different. If I actually take 80% confident, I find they're all different by 20%. What I think is really, really cool or fundamental is one of these is actually a quantum computer. The rest of them are what we in the field call tensor methods. So it's not that quantum, when we say, what we concluded in this paper is we're at a point where we're beyond brute force, so there's no exact simulation of this. Every one of the tensor methods converge to a different answer. None of them converge to the same answer, and quantum is one of them. So you can kind of start to see it as a numerical tool where you can start to explore, start to use it to explore scientific applications. For the experts in the field, some of these numerical methods are new methods that have been invented, so new tensor methods, that the convergence of the method is based on converging to the experiment. So what that means is we've got at the point where a quantum computer is actually getting at the point to test classical methods of converging. And so they don't have formal convergence, but they test their convergence based on converging to the experiment. So that's one. We can start to do this interesting type of experiment. Second is users. So if you want to get good things run on quantum computers, if we plot the number of the average, so I'll plot here years down the bottom, and then I'll plot the average number of qubits people are using, okay? If we plot, since we put the first quantum computer on the cloud, how many qubits people were using, you see that it follows this weak, quadratic formula where the blues start at like 5 qubits and gets up to 13 qubits, okay? So before 2023, before the results of that experiment I just showed, I would say that even if people had access to 100 qubits, they were only using a handful of them. What has changed is, like I said, we got to the point where we can go utility. So here I've plotted all the different quantum hardware that you can find that has numbers in the public domain. In blue are the IBM hardware, and then the dotted line is what I call utility, where if you think of the number of qubits, it's either got to be above 100 qubits, above 1,000 gates. You got to be in that regime for you to be doing something that is outside doing classical. So the first is the hardware has got to that region. Second is the software has got to the point that is very performant. Just to give some numbers, Qiskit now runs, the updates means execution on the quantum computer runs about 70 times faster than it did before. We can do accurate gates up to 5,000. We've developed software that can mix classical and quantum together so we can explore those type of algorithms I said at the start. And we've got to the point that we can compile to these systems these long circuits, and we can get shorter ones that run. So the big two things that have changed is the hardware and the software. And if you put that together, what we find is the usage of these systems has spiked, where the average usage of the quantum computers now, using the latest hardware, is getting up to above 100 qubits. And this is a combination of this, this is why I'm kind of excited about this, is we've got to this point where we are actually starting to use them, where we can no longer simply simulate them. And then there's been many, many different papers that are published in what we call this new regime of doing large simulations. I just show a handful of them here, as well as some more here. So if we'll take a step back and say, even though we have a long-term plan of getting to an error-corrected quantum computer, and we need to, in my view, demonstrate a scientific examples of quantum advantage in the near term, what are 3 things that I think are required for this? What are the things that you need? First is obviously you need a system that is beyond being classical simulated. Second is you need a dedicated community of algorithm researchers. And third, you need a set of methods that can provide accurate executions. I call this error mitigation, error detection, and even correction. I'll explain what I mean by that. And this third one is, I think, the most important. I'll spend as much time as I can on explaining the third one. Actually, I stand corrected. All 3 of these are all important. But the third one is not as appreciated enough, and I'll try and explain what I mean by that. So first, I'm very proud of the fact that in Korea, we have now a system of this size. There's a picture of the Yonsei system that we just did the opening ceremony, as well as some of the other ones that are around the world. So as I said, the first is you need access to a computer that can be of this size and quality. Second is you really need this commitment of algorithm developers to explore using these machines in novel ways. At IBM, we've really focused on everything from how we start to create easy content, so courses to get started in quantum computing, as well as taking, videos to get started, as well as taking courses, as well as taking credentials to get certified. And then finally, as I said, many, many papers have been published using these machines. I am actually very proud of what has already been done in Korea. I actually think since the system got installed here, it is the fastest growing of using the systems that we've ever installed. That says something about the quality of the researchers, the quality of the students that want to get using it. It is actually, I'm very impressed by how fast. So Yonsei has started out really well training, getting these type of courses, and we're really seeing that pick up. And I think as we go forward, I totally, with all the partnerships that we've done, I totally see Korea being on the global stage in using it. So first, having a system, having the ecosystem of algorithms. So what is the third? So the third is, how do you trust a near-term device? Or how do you trust the output? Or how can you be sure that it's executing something that you can start to define quantum advantage? So quantum computers, at its most fundamental, is you run a circuit and you sample an output, okay? Scott Aronson has a beautiful paper that can show random circuits are actually hard to simulate. If you go a deep down, actually there's been a lot of work that has sort of shown that you can't actually verify that output. So if you want to have a problem where you sample and you want to confirm it's working, you either need to have some simple way of verifying it. That being said, there are ideas emerging now by Scott Aronson and others of how to put some type of peak in to solve the verification problem. But secondly, because this could still be noisy, some of the computational hardness starts to disappear. And for these type of random circuits, I don't accept that they are a viable demonstration of supremacy or advantage, depending on your word, because they are built fundamentally without the trust that the quantum computer is executing what the theory paper said. So what we started and what we pushed forward in this near term, and I'm starting to see it get much more rigorous, is this concept of error mitigation. And I'll try and generalize it as I go forward. So now, rather than send just one circuit, you send a circuit plus an observable, okay? Now, what happens here is now because there's a well-defined theory, you can actually be confident that the result that is coming out of the quantum computer has error bars that I can propagate forward. The cons of it is this takes exponential time to run. Second con of it is people have pointed out that possibly polynomial classical algorithms exist. So if you've got something that takes exponential and polynomial, you might first start to be a bit worried. And the third, which is kind of one of the ones that I think needs to be explored more, is now because you contract it down to observables, the hardness of this disappears. And in the example I showed before, you have to compare it to tensor methods, and it gets harder to say. So starting with the error bars. I'm not going to go through the theory, other than to say essentially the experiment consists of running a unitary, some noise happens, you recover the noise, you run the unitary, noise happens, you recover it, and there's a way that you can bound this recovery with this simple formula here, and you see it has this gamma bar to the ND that's exponential. You can propagate this all the way through to give you the error bars. And like I said, many have pointed it out to be exponential, but when you start to put the numbers in, you can take something that's polynomial, something that's exponential, and you can find that if you're doing small enough circuits that are still not up to the limit of running the algorithms that we want to run long term, but are nevertheless past the place where you can simulate them easy, you actually get numbers that allow you to actually look at it. And that's exactly what we've started to see in the last few years. What we've seen is that experiment in 2023, then 2024, we were able to take it from 2,000 to 5,000 gates and show that you could get most of the accuracy of the observables still there. And then it's not just ourselves, it's also Algorithmic Q as a company, as a research company out of Finland, where they've come up with their own ways of doing this type of, their own version of error mitigation to propagate it forward using tensor methods on just the errors, so they can bound how that propagates. Kedma, which is a company out of Israel, has their own form of error mitigation where they can give you an unbiased estimate, control the errors, and propagate it through. And so you see that there's these sort of methods that are emerging that give you these error bars that allow it to propagate. Now I want to sort of show, next interesting, is you can start to think of this as a continuum from the error mitigation, where you take many runs, to many qubits, obviously a fault-tolerant quantum computer that exists. So what we argue is as we build these tools, you're going to see this continuous path, right? That you build trust into these methods to allow you to run bigger and bigger experiments. So now, error mitigation itself was rigorous, gives you error bars. Can you start to add error detection to it? Can you add ways of doing error detection? And the answer turns out to be true. So in an early paper by Sergey, myself, and a few others, we came up with a way we call Pauli checks. And what we were able to show is you could run some payload, and if you did checks just at the end, you could propagate through and post-select the output. But now what people have learned is you can start to, we call them space-time checks. Rather than just check at the end, check continuously through it. And so what I plotted down on the bottom is because there's a post-selection, you have to select when the output happens, whether you keep it. You see the difference between the write-only checks and the space-time checks. For the post-selection, you see it's like 1,000 times better if you can do this sort of space-time check in terms of how many samples you can keep before you actually need to reject them. You find the fidelity is about 70 times better. And because you actually use less checks, there's a lot less gates that are using to do it. So this idea of putting error detection, and I'm going to show you results that we haven't actually shown anyone before, is now you can start to do ridiculously big Cliffords that you can create arbitrary graph states, mixing ideas of checks to get that trust back into the machine that allows you to create with high fidelity. So look at the green here is for 14 encoded qubits. Post-selected it's going up after around 6 checks, close to 1. But this all goes down to the red, that you can even see it going up to 50 qubits for these large graph states that really start to give you a feel for ways that you could really push this into the future. And all of this is possible if you have access to the machines. You can start to explore this. So the way I kind of want to sum it up is I actually think that there's a continuous path from where we are today to where we get to many qubits to do fault-tolerant quantum computing. If you build methods based on trust, you can start to explore for those scientific algorithms. You can start to explore those scientific use cases in chemistry, biology, materials, based on circuits that you know cannot be simulated. I love this quote by Feynman Dyson that says, "Scientific revolutions are more often driven by new tools than new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have yet to be explained." Where we are right now with quantum computing is we can start to run circuits that are at a point we cannot simulate them. So the question remains, how do we actually use them for searching for applications? Just to conclude, now if you've got this trust, you can start to build chemistry, machine learning, optimization, algorithms on top. Our view at IBM is to work with everyone. If you create your own algorithm, you're going to build it on top. And for example, many of these application functions are available online and remote, and some that are actually coming out that I think are quite nice is that extend the original ones by Q-Control, Multiverse, and Quinasis. These are ones by Kapu, which looks at optimization problems, and they're getting to a very large size. And Quinova, which is actually a Korean startup company, has done some nice results that show that built upon these methods, they can start to do interesting chemistry-type simulations. So on that, I'll conclude and say the reason why I think advantage can happen is because of those three things: access to hardware, the development of a community of algorithm researchers that are dedicated to solving hard problems, and the development of tools that allow us to execute quantum circuits of a large size that we can trust the outputs. Thank you.
We don't have much time, but maybe you can ask a very short and very urgent question. One question. Anyone? No? Then you can ask a question during the break. Thank you.
Thanks.
Let's thank our superconductor again. And it is my pleasure to introduce our next speaker, Professor Kyung-Hyun Baek. Kyung-Hyun Baek earned his PhD in theoretical quantum information science from Seogang University. He then pursued postdoctoral research at Texas A&M University at Qatar and the Asia Pacific Center for Theoretical Physics and the Korea Institute for Advanced Study. Following these positions, he joined ETRI, which is the Electronics and Telecommunications Research Institute, as a senior researcher. And most recently, Professor Baek joined Yonsei University just a few months ago, bringing his expertise in quantum information science to Yonsei University. Today, he will be presenting on subspace time evolution in parameterized quantum circuit. Let's welcome Professor Baek.
Yeah, thank you for the introduction. And as a member of Yonsei University, I would like to thank you all the audience and speakers participating in this conference. So, and I'm also very honored to have this opportunity to present some recent result. So today, I will talk about the subspace time evolution in parameterized quantum circuit. So this work is established based on the variational quantum algorithm framework. So I think many of in the audience are already familiar with this this framework. So I'll briefly introduce this concept, and then I'll introduce our main result, and I'll show you some examples, Ising model, 2-qubit Ising model, and 10-qubit models. However, I'm very happy to present some experimental data obtained by the Yonsei University IBM quantum processor. So, yeah. So, and then I'll conclude with some summary. So, as I said, our work is developed based on the framework of a variational quantum algorithm that is also known as VQA. So VQA is composed of those 4 steps. So at the first time, we should prepare some quantum states in the circuit, and then we measure some observables and estimation to estimate cost function. And then by using those some experimental data, we can classically perform some post-processing, such as averaging over those data. And also we performed some classical optimization. Actually, those classical optimization is already developed in machine learning or other some numerical techniques, such as a gradient descent. Yeah, so in this sense, the VQA, when we implement those VQA, we should, quantum computer is dedicated to obtain a prepared quantum state and estimate cost function, because quantum computer provides some exponential speed up or some efficient method to perform those 2 steps. And by how, on the other hand, a classical computer can dedicate to perform those 3rd and 4th step. So VQA has many applications, because by some adjusting some cost functions, we can apply this method to various fields. Actually, at the first time, the variational quantum eigensolver was introduced to attack the ground energy estimation. That is so-called variational quantum eigensolver. And then this framework is extended to attack other some very challenging problems, such as applied mathematics and some quantum machine learning and some quantum dynamics. So in this talk, I would like to focus on this quantum dynamics problem. Yeah. And however, I think recently there are many researchers are working on the verifying some complexity of this VQA. However, fundamentally, it is very challenging to verify how much computing resource are required to perform this VQA, and there is a quantum advantage or not. Yeah, there are many challenges. That is because this method is, depends on the choice of ansatz and then some optimization techniques. And also there are many problems or challenges in those, such as local minima. So even if the optimization procedure is finished, actually we cannot say that it's definitely global minimum. So as far as I know, I think it's also another very hard, difficult problem to verify that. And also another some noise effect or some cost function estimation is also very critical. However, the most recently many researchers are focusing on to investigate how much balance plateau has occurred during this optimization. Because if there is a balance plateau, exponential increase of sample complexity is required. So, I would like to remark that in this sense, when we implement VQA, we should care about those factors, including our method. So in the quantum simulation, actually, at the first place, Feynman conjectured that quantum computer can be useful to simulate some quantum systems. And so Seth-Lloyd proved that the quantum computer can efficiently simulate those kind of some Hamiltonians. And then some other approaches has been developed to cover some various type of Hamiltonians, and also another so reduce the complexity. However, in this work, we will focus on this totalization because it is relatively easier than other methods, and also it's very intuitively we can implement in real hardware. So, for instance, in the Ising model, the totalization is very intuitive because Ising model can be described in this way: two-body interaction and single just rotation. So in the first order totalization, each local Hamiltonian can be performed just in this way, decompose Hamiltonian into local Hamiltonian, and we perform those interactions. And so each interactions can be also implemented in the real hardware by using those quantum gates. And so, if we implement those totalizations in real hardware, the quantum circuit would be like this. So we prepare some initial state U0, and then we perform those total step and repeat again until it achieves some target precision. However, as far as I know, I think it is still difficult to implement this totalization in real hardware. So variational quantum algorithm is developed to reduce that kind of a computing resource. So our main concept is that we prepare some initial state first, and then we apply a parameterized quantum circuit here. Then we implement the totalization step only one. Then only one or two, so it depends on some quality of hardware. So after we implement apply this total step, then the state is evolved to some state that is evolved to within the time delta t, because we decompose the total time evolution into some small time step delta t. So, however, if we repeat this total step, I think it would be very many noises involved. So we introduced the inverse of initial state preparation. Then by measuring in computational basis, then we can obtain the fidelity. The fidelity corresponds to the probability of obtaining these all zero outcomes. So the reason why we pick up this fidelity as some numerically investigating the distance between two states is because that the fidelity is relatively simpler than other distance. So our cost function looks like this. So by optimizing this phi to minimize this fidelity, and then we obtain some final value parameters, and then that parameter can be used to prepare the new state. But this new state is close to this evolved state. However, I would like to remark that this kind of method is not my own idea. Already there are many previous works to attack this kind of approach. However, our main point is that the previous works mostly focus on the time evolution of just one initial state. So if we want to simulate another state, we need to repeat the whole procedures. So we would like to develop some method to simulate a subspace expanded by those some orthogonal base. So in order to do that, we need some more circuits. So first of all, we prepare the one over basis of psi 0 here, and then we repeat the same as the previous circuit. And however, we need more circuit to cover the subspace. So we prepare another psi 1, the U1, by applying the U1 unitary. However, the rest of the circuit should be the same as this one in order to cover at the same time. And additionally, in order to adjust some update properly the phase of between two states, so we need to introduce the psi plus, that is purple state of psi 0 and psi 1. And the total host function is defined as in this way. So the first part is dedicated to allow us to simulate this first column, and the second second fidelity is dedicated to find the optimal value, optimal those column vector. And the third one is important to adjust this phase vector. Then by optimizing at the same time, we can cover all the subspace. That means alpha psi 0 and beta psi 1. Every arbitrary state in this subspace can be simulated in the optimized parameter quantum circuit. So one of the particular some positive aspect of this method is that we can verify the quality of this optimization procedure. So as far as I know, the user just VQA have no those kind of some lower bound, the performance of lower bound. Because that, as I said before, we don't know that the solution is in local minimum or global minimum. However, in this case, our cost function is composed of those fidelity. So we know that the fidelity is the limited, the maximum fidelity is 1. So by considering all the data obtained during this optimization procedure, then we can obtain the final fidelity of the lower bound of fidelity that obtained by the parameterized quantum circuit. So yeah, that is some positive point of our method. And then we can generalize to arbitrary some subspace. Yeah, if the dimension, the number of base expanding this subspace is n, then the total fidelity that we have to measure, fidelity is the number of this fidelity is 2n minus 1. So yeah, it linearly increases with respect to the number of bases. So it's our some preliminary result. So we test in Ising model, 2-qubit Ising model. So as you can see, if we perform the subspace, we assume that our ansatz is SU4 for 2-qubit. That means it is perfectly express all the states in 2-qubit. So yeah, that expressibility is maximum. Yeah, in this case, the subspace time evolution shows the maximum fidelity 1. So all the fidelity are overlapped here. So we just can see that some one line. However, all the fidelity, including psi 1, psi 0, all fidelity are 1. However, if we only optimize for just one initial state, then other states, such as if we focus on the 0, state time evolution, then 1, state is not evolved perfectly. So that means it's almost random. So that's the reason why we have to care about the subspace time evolution. So if we restrict our some expressibility of ansatz by just the GXG and C0 gate, and in that case, the fidelity is decreasing as time is increasing. So yeah, that's because of the limited expressibility of this ansatz. So this is our some IBM quantum processor result. So we performed the 2-qubit experiment in Yonsei University IBM quantum processor. Yeah, and then we almost we demonstrate the experimental result, almost followed some simulation. And so another application of our method is that we can, by optimizing the parameterized quantum circuit, just one whole procedures, we can generate all arbitrary state in subspace. So we tested by from 0, state, 1, state. So I think it's very small, but the x-axis is time, and the y-axis is theta over 2-qubit state, 0, plus and 1. So when it has theta is 0, then there is no entanglement here. However, when it is pi over 2, entanglement is maximized, and then it disappears. So this is the exact solution, and this is the result from throttlization. That means just the emulation result. Then is experimental result. So I think it's very coincide with some numerical data. Yeah. So what I want to emphasize in this result is that we can apply those some already developed method. So if we want to investigate some entanglement dynamics, so we need to compute any state. We need to compute numerically. However, if we can prepare a quantum state in quantum circuit, then we can perform those techniques. So in this sense, it is just a constant depth to estimate the entanglement. So just we optimize, finish the whole optimization procedure, and then we can explore any arbitrary state, entanglement of arbitrary state in this subspace. So, yeah, we considered some more entanglement, some more qubit case. So we 10-qubit hardware and 10-qubit Ising model. So in the our ansatz is defined in this way, and yeah, I just skip. Yeah. So yeah, it's the it shows the whole procedure. So yeah, it's from 1 layer to 5 layer. Actually, according to the number of layer, we can adjust some expressibility of ansatz. So yeah, we can expect that because of expressibility, so 1 layer ansatz, its fidelity is decreased very fast. Yeah, however, by increasing the number of layer, we can see that the fidelity is stable, almost around 0.98. Yeah. So yeah, I'd like to summarize. So we developed some variational quantum method quantum algorithm for simulating the time evolution of a subspace, and we test it in some Ising model and IBM's quantum processor. And there may be some open questions. So can we, a relationship between the number of qubits and needed layers to achieve high fidelity, and finding a better answers based on the symmetry in Hamiltonian. Thank you for the attention.
Thank you, Dr. Beck. And any urgent and short question? No? Okay, then you can think of some questions for the break. Okay, thank you. And the next speaker, our final speaker for this session is Murray Tam, Vice President of Quantum Technology Evangelism at D-Wave. So actually, I myself am a quantum evangelist in Korea, and now he has a department of quantum technology evangelism. With over 20 years of experience in quantum computing, he has been deeply involved in the evolution of the field. D-Wave's quantum computers differ from the IBM-style gate-based approach. Instead, they use quantum annealing, leveraging thousands of qubits to excel in specific optimization problems. That's what I know. Remarkably, Murray was even hands-on in assembling some of the early quantum computers by himself. Today, he will be discussing the return on investment, ROI, of quantum business applications, focusing on their transition toward real-world production and commercial impacts. Let's welcome Murray Tam.
Thank you, everyone, and thank you, Dr. Kim and Dr. Chung, for hosting this event. I'm really excited to be here with all of you. Now, how many of you were at the reception dinner last night? I was there. Was anybody else at the reception dinner last night? There was a fantastic band who were playing traditional Korean music and modern Korean music, and they were singing songs about love, and the theme of this event is quantum love, right? And the E in quantum love is engagement. So we're going to try what that band was doing last night. We're going to try a little engagement. I would like everyone in the room to just lift your hand. Raise your hand for me. Everyone, there's no qualifying criteria. You just raise your hand, and we got our hands up. Okay, now put your hands back down. How many of you now are quantum physicists? All right, we got Charles in the front and a couple in the back. Okay, great. Honey, yeah, good to see you. All right, how many of you are in the Department of Computer Science? Quite a few. Okay, how many from mathematics? We've got some mathematicians here. And statistics? Anyone from statistics? And anyone working on machine learning, artificial intelligence techniques? We've got a few of those as well. And then in terms of the life sciences and pharmaceutical sciences? Up front, all right, great. Okay, so everyone who did not put up their hands for quantum physicist, this presentation is for you. Okay, and I'd like to see a little quantum love. Everyone put up a heart here. Let's see your quantum love. I learned this heart technique last night. All right, so quantum technology evangelism is my role. I help global businesses and organizations to understand quantum computing and the transformational impact that it can have for them today. I'm really excited to be with you here. I'm not going to spend a lot of time talking about this slide, but it gives you a bit of an idea about D-Wave. We were the first to commercialize quantum computing systems, and we're also the first quantum computing company that has customers who are running applications that are quantum hybridized as part of their production operations. All right, so I'm going to begin at the beginning. What is a quantum computer? Right? It's a device that uses quantum effects to perform calculations that are too slow or too hard for classical computing systems. Okay, so that means that quantum effects must be a resource for the computer. What kind of a resource does that actually represent? Well, it turns out that we've determined multiple ways to use quantum effects as a resource in a computer, and those are the different models of quantum computing. D-Wave is the only company that is building two primary models of quantum computing. And I'm going to be talking to you a lot about annealing because that is the area we began with. So let's look at annealing. There, quantum effects is a resource that allows the computer to move between solutions more quickly. So let's say you're a business and you're doing at-home grocery delivery driving, and you want to assign schedules to your workforce. Well, you might have a current schedule that you're working with, and what you'd like to do is transition to a better schedule. So you want to make that state change faster. That's the idea behind using quantum effects and annealing. Now let's contrast that with gate model. In gate model, we're using the quantum effects to allow the computer to store more information. It turns out that the choice that we make about how we want to use quantum effects as a resource for computing determines what skills we need to program the systems, how quick it is to develop the systems and build the hardware, and also the applications that they're going to be useful for. Because what we now know from the research community is that if we want to tackle problems in quantum optimization, we must have annealing quantum computers. The reason for that is because the overhead for using a gate model system is too high. But we also know that there are very important applications in quantum chemistry and in 3D fluid dynamics, fluid flow calculations, that we can only do with gate model systems. So in the future, we're actually going to need both of these quantum computing models in order to be able to provide the full suite of calculations that quantum computers can do faster than classical computers can. Okay. Now, I'm going to be talking for most of the rest of the presentation about D-Wave's mature commercial quantum annealing quantum processors. These are some of the most studied quantum computers on the planet. There have been nearly 10,000 research papers published on D-Wave quantum computers, and more than 150 of those have been published in Science and Nature portfolio publications. In fact, we've crossed over the point of having 1,300 publications per year. But what's significant about that, and like the survey I did at the beginning of this, we're engaging young, talented researchers in the areas of computer science, mathematics, and statistics, because you don't need to know quantum physics to program quantum annealing systems and put them to use in applications. So in fact, it's a very complementary technology to the center here that's doing work with the IBM quantum computing system. Now, I've been asked from time to time, what is the most significant development in quantum computing in the last year? And this is my answer. This is information processing beyond classical computing that is incredibly energy efficient. We published a preprint where we were able to demonstrate a calculation that we could do on our quantum computers in 20 minutes that would take a high-performance computer more than 1 million years. Now, some of the members of my quantum computing community use the term high-performance computer a little loosely, but I'm using it in the formal sense here. We used 100,000 hours on the Frontier and Summit supercomputers at Oak Ridge. The Frontier supercomputer is the largest supercomputer on the planet right now, in order to do these calculations. And we were able to do these calculations here on the systems at small scale. We chose a problem that has been well studied so that we knew exactly how the difficulty would scale with the system size. And then we were able to project how much effort would have been required to match the results we were getting with the quantum processor. And this threshold here is 1 million years on that Frontier supercomputer. Now here's the key point. D-Wave has produced 5 generations of commercial quantum annealing processors. Every single one of those generations of commercial quantum processors consumes 15 kilowatts of power. That's about as much power as we're using in this room right now. For a high-performance computing system, that's incredibly low power. So while all of the CPUs and GPUs that we're using have been steadily growing in their energy consumption, why is it that these commercial quantum processors are not growing in their energy consumption? It's because the quantum annealing processors that are made out of superconducting metals at their core consume 1 million times less power than a mobile phone. So what this indicates is that if we can take workloads that are very difficult for high-performance computing systems in the areas of material research, in the areas of optimization, industrial optimization, and in the areas of artificial intelligence methods, if we can take those very difficult calculations for classical computers and move them onto these quantum computers, we can dramatically reduce the energy consumption for those calculations, which is a pivotal issue in the world today. Now, the kind of work that you're doing here at Yonsei is absolutely critical. And there are a community of other high-performance computing and computing universities who are similarly doing what you're doing. So at the Forschungszentrum Jülich, the Jülich Supercomputing Center, they've purchased one of our annealing quantum computers, which they expect to connect to their Jupiter supercomputer, Europe's first exascale HPC. And this is a photo of the D-Wave quantum computer currently at their site in Germany. Their focus is going to be on using these quantum computing systems for modeling and emulation, and also for provisioning quantum computing systems, much as you're doing here in the Korean region, to study the integration of high-performance computing systems and quantum computers in terms of how they work effectively together, and to create quantum computing user infrastructure for science and industry. Now, they have a model which includes having on-site both annealing quantum computers and gate quantum computers, because they also recognize that there are different uses for those two technologies. And so as they want to engage their full community, they can do that by supplying those users with a variety of quantum computing systems that are complementary to one another. Now, this is a pivotal moment in the quantum computing industry, and D-Wave is focusing on shifting the conversation away from experimentation. Yes, there is some very valuable experimentation that still can be done. We need the research community to explore and answer open questions that those of us in the industry of building quantum computers don't have the resources to tackle. But we also can now start talking about conversations about the operational use of quantum computers by businesses. In order to do that, we don't have to talk about toy problems. We can talk about problems at enterprise scale. They're full application problems. And we don't have to just talk about the potential impact in the future. There is tremendous impact in the future for quantum computers. We can talk about our return on investment that those businesses can measure today in their operations. So let's talk about some of those use cases. The first is Pattison Food Group. Pattison Food Group owns 13 different grocery brands in Western Canada. During the pandemic, we began working with them because at-home grocery delivery became incredibly important to their business because a lot of their customers couldn't necessarily come into stores to do their shopping. And we worked with them to help develop an application to produce the schedules for those at-home grocery delivery drivers. And when we did, we were able to reduce the scheduling time by 80%. That application has been in production since October 2022. So right now, there is a full-time application running at Pattison Food Group for these delivery drivers, and it's just been running continuously since 2022. Since then, they expanded to a second application in their stores to tackle a difficult problem. They have machine learning methods that give them a forecast of how many customers are going to be coming in each day of the week and each week of the year. And then they have to schedule their employees in store in the different departments based on their seniority, and they have to optimize a full work week for their employees. That is now an application that they have built, they've tested, they're taking it through their first phase of release, and they're already at the stage where they're expecting to save their workforce 50,000 hours every year. So the great thing about these applications we can use these quantum computers for is that applied in businesses at scale, they have a tremendous impact. And when we talk about return on investment for quantum applications, we have to consider everything in terms of their operations, their workflow, the impact on their people and processes, and that has been achieved here. What's really significant about that second application is that the team members who were responsible for scheduling, they were the most senior employees at the company. And they had to spend dozens of hours behind their computers each week working on these schedules. Well, now they don't have to. They're able to actually get out and work with their more junior employees and train them on the important elements of their business and work directly with their customers. So a really significant impact on their employees and their business in terms of their business processes. Now, you may have heard about this example. NTT Docomo in Japan has used our quantum computing systems to optimize their mobile telecommunications networks, specifically the paging signals that pass between the base stations and us as cell phone users. They've been able to reduce the number of paging signals that are needed in the network during peak loads by 15%. And they are currently scaling this application out for full production use in Japan nationwide across 250,000 base stations. So a very significant network that this is being used in. And it effectively increases the capacity of that network by 15%. Now let me talk to you about this third example Ford Otosan in Turkey is looking at their Ford transit line and the production of the vehicles on that line as the conditions change. They want to be able to schedule which equipment is used for manufacturing their parts and their vehicles so that the whole production line is as productive as possible. And we were able to work with them to allow them to schedule 1,000 vehicles in 5 minutes, an 83% savings from their previous 30-minute time, and it also reduces the number of business constraints that were violated in those solutions. Now, this application is yet to move on to full production, but it has been tested in their production line, and they know that they can get a high return on investment with this application. Okay, so let's talk about, those are some of the examples of applications that are currently being used, are currently running and have been running for years, and are on their way towards moving in production. There's so many exciting applications. We've got literally 100 organizations around the world who trust D-Wave to use our quantum computing systems and bring them value because we have the performance, the reliability, and the use cases to allow them to apply this to their business and see value now. And that's why we're all looking to quantum computing, not just for exploring the science behind the systems, but actually to bring productivity, efficiency, and efficient energy use to our economy and our nations. In order to support these applications, D-Wave has produced 5 generations of commercial quantum processors. Those are the advantage quantum computers. We've also have a cloud service called L.O.V.E. And this is the system that has the high reliability. Its availability is 99.9% of the time. We could get online right now, submit problems. When we're submitting problems to the QPUs, we can get sub-second response times immediately as we're programming them. In that system, we've also got these ocean open source tools. And the open source is really valuable both for businesses, because it allows them to inspect the application code and make sure that it's secure, but also for this community, this broad community from different fields. Because the quantum physicists will start programming the systems at the low machine instruction layer. But the mathematicians and computer scientists may be coming in at the middle layer. And then the software developers and application developers and industry will coming in at the top layer. And as each of those communities contributes to that open source library, we get a compounding benefit for the businesses that are building applications on top of it. And at D-Wave, we also have a program for helping folks wherever they are on their journey from discovering which applications are suitable for quantum computing, because it's important to note, although we could submit any kind of problem that a classical computer could do to these quantum computers, they can't accelerate all problems. We just want to focus on the problems that they can accelerate. And once we've identified those, then we want to start rapidly building proof of concepts and then moving them to production. We have a worldwide network of quantum computers online right now. We have systems that are in Burnaby, Canada, also at the University of Southern California in Los Angeles. I talked to you earlier on about the system at ULIC, Germany, and there's a new system going in Huntsville, Alabama, a little bit later this year. Now, one of the important areas of research, it's actually been pivotal and critical for the use of quantum computing systems, has been the hybridization of classical and quantum computers. When I first started coming out and meeting with users, I was teaching them about the machine instructions for our quantum computers and to help them hybridize the systems. We even created an entire open source library to show users how to hybridize classical and quantum computers productively. But the response from our customers was, hey, that's great, and I love that it's open source, but we don't want to have to become experts in those algorithms. We want to solve our business problems. So we've actually developed online hybrid solvers here that are allowing people to tackle enterprise scale problems much more quickly. It makes the program development much faster. It has high availability. And as we produce new quantum processors, and they have dramatic performance scaling relative to the previous generations, all of the customers running on these hybrid methods get the benefit of that evolution. Because the hybrid solvers take in their large problems, they begin working on them with classical computers, and those classical computers break pieces out and call the quantum computers on the customer's behalf in order to help it move through the solution space and find high-quality solutions quickly. Okay, I'll finish on this slide with a minute and a half left. We have our user group meeting at Qubits 2025. We're talking about realized quantum applications, March 31st and April 1st in Scottsdale, so hopefully some of you will be able to attend. Check it out online, and yeah, maybe we'll have time for a couple questions.
Do you have any questions? I want to ask a question.
Please.
So some years ago, there were some comparisons going on between the coherence-icing machine and quantum annealing machines. So do you have some saying on this?
Well, after some of that initial work, the results began to fade away. So I saw less and less development from the coherent icing machines. I'm not sure if they continued that project. For the folks that I know in optimization algorithm development, the coherent icing machine looked like a mean field solver. And that's a very valuable solver if it can be accelerated, but it's also something that classical computers can already do very effectively. Whereas in the benchmarking tests against our quantum computers, we've actually found that they're able to solve problems that classical computers find very difficult.
And also D-wave is from the high temperature superconductivity, right? And do you use this high temperature superconductor?
No, a little bit of trivia here. So the founders of D-Wave were members of the high temperature superconducting community. They actually designed their first qubit using high temperature superconductors, which use D-Wave superconducting wave functions. But that design didn't turn out to be the one used in the production, but we kept the name. So we're still using low temperature systems, which is S-wave superconductivity.
So historically.
Yeah, historically, yeah, that's right.
And another thing is, I'm not familiar with your system, so is there some kind of metric like a quantum volume to evaluate the performance of your system?
Well, the difficulty with quantum volume, which is really just the number of qubits multiplied by the connectivity and its coherence, is that there isn't really a close connection between that and then the results we see in applications. So that's why I put the focus today on the benefits that people have seen once that technology has been put right into their application workflow. However, we do have a whole series of benchmarking publications, both individually proving quantum mechanics is accelerating it and against classical computing systems. So if you've got questions, if you'd like those references, come and talk to me afterwards and I can send them to you.
Okay, thank you. Any other questions? Okay, let's thank our speaker again.
Thank you very much.
And we are going to resume at 3:05. Have a 15-minute break. Thank you.
After 15-minute break, we will proceed the second session at 3:05. See you shortly. Thank you.
The International Conference Session 5 will begin shortly at 3:05. Please take your seats. 곧 3시 5분에 세션 5 시작합니다. 자리에 착석 부탁드립니다. May I ask your attention, please? The International Conference Session 5 will begin shortly at 3:05. Please take your seats. 3시 5분에 곧 세션 5 시작합니다. 자리에 착석 부탁드립니다. Attention, please. The International Conference will begin soon. Please take your seats. 세션 5 시작 시간 살짝 지났습니다. 자리에 빠르게 앉아주시기 바랍니다. Next, we will proceed with International Conference Session 5 with Professor Daniel Kyung-Tok-Park. Please welcome him.
Thank you, everyone, and welcome back to the session two, okay, the second session of the today, but the session number is 5, right? So session 5, quantum computing and networks. So yes, it's my great honor to moderate this session and also introduce the speakers to you. So the first speaker for this session is Dr. Charles Bennett from IBM. He's going to tell us about quantum information's birth, growth, and impact on fundamental questions. Please join me in welcoming Dr. Charles Bennett.
I'll just tuck this into my buttonhole here. I was going to talk about the early history of quantum information science when it was not anybody's day job to do it. And this is a picture from what I consider one of the formative conferences. It took place in 1981 at MIT, and it had about 40 or 50 people, including some Nobel laureate, or I guess just one Nobel laureate, Feynman, but a number of other people of similar stature, and at least one extremely peculiar person, who's right here. You can see here he is. He's Fred Cantor, and he would explain to us that he had a peculiar form of dyslexia that required him to speak very softly and very slowly. And he would sometimes forget his name, but he took care of that because you see it's printed on his shirt upside down so he can look like that. Anyway, he was one of the people there. And this was quite a day. So I'm going to talk about the very earliest history of the field. And I'm also going to try to talk about it in a way that if you are not, I guess you were one of the people who didn't hold up your hands, because it's important in this field for people to understand it, not in a way to practice it, but in a way to have an intuitive understanding of quantum information, so they can avoid irrational exuberance, or they'll be able to see what's likely to be true rather than to be either intimidated or over-enthusiastic and not know, to develop some common sense or good taste about quantum things. Now, speaking of not my job or not our day job, I'm going to say something a little depressing. And that is, people around here often ask, is quantum computing or is quantum the next big thing? And it's not any of our day jobs, but technologists often forget that the next big thing is often not technological. In 1929, it was a financial collapse. In 1939, it was a war. Maybe some of you are too young to have been alive during that war. In 2019, it was a pandemic, and maybe this year it's a period of geopolitical strife and economic fragmentation and so on. Maybe so bad that it kind of eclipses the world that we're used to, where we walk around with these miraculous machines in our pocket, which maybe the world will be too disorganized to make them anymore. And we have to go through a period where we look back on the glory days of technology for a few years before we get our act together again. But that's not anybody's day job, but I guess it's in the back of everybody's mind to try to preserve what we have or maybe improve it. Now I'm going to go on and try to explain, to make quantum information, quantum computation seem more natural, intuitive and easy to understand for somebody who's had, I'm going to try to explain it in a way that doesn't need anything more than high school algebra. But fundamentally, like other parts of mathematics, information science originated in abstractions from everyday experience, especially Turing's abstraction, a universal hardware-independent notion of computing, which has pretty much been absorbed into common sense. And even more revolutionary was Shannon's meaning-independent notion of communication. Now, like, what could be more obviously crazy than that idea? But yet it turned to be very fruitful. So we're still in the middle of the information revolution, which sort of began around the time I was born and still is going at full steam. Now, it's one of the outstanding features of it is that even lay people are familiar with the content of Turing's 1935 paper. Was it 35 or 36? So around then. Essentially, they understand computational universality when they say, go into a computer store and say, well, do you have this app for my Mac? And they also understand the fundamentals of what Shannon discovered with in information correction and error correction and data compression. But chemists and physicists have long known that information doesn't behave in the way that's entirely described by the principles of Shannon and Turing. And this was the thing that was belatedly understood, began to be understood in the 1960s and 1970s. And I'm going to talk about that. But first I'm going to say, how do you explain this in an elevator or at a cocktail party? And when you start talking about vectors in Hilbert space, people get to glaze over and they don't want to listen to you anymore. So I find it helpful to say that everybody understands what ordinary information is, but quantum information is more like the information in a dream. And if you try to describe your dream, it changes your memory of it. And so eventually you forget the dream and you only remember what you said about it. And you can't prove to somebody what you dreamed. And you can lie about your dream without getting caught, unless you try to lie to your spouse about it. But unlike dreams, quantum information has well-known laws. And despite these differences, there are important similarities between classical and quantum information. And this was not noticed really because of the success of Turing and Shannon. That is, people were thinking of information as classical information, and quantum information is just a kind of unreliable kind of classical information, which you could deal with the tools that Shannon gave us for error correction. I'm going to get to that slide a little bit later. But the central principle of quantum mechanics is the superposition principle. And this is that as between any two reliably distinguishable states of a physical system, there are intermediate states that are not even in principle reliably distinguishable from either one. And that mathematically these the possible states of a physical system correspond to directions in space, not ordinarily three-dimensional space, but a space that has as many dimensions as the system's maximum number of reliably distinguishable states. In any direction is a possible state, but two states are reliably distinguishable if and only if their directions are perpendicular. Now, this tries to put it in mathematical terms that are understandable to high school algebra, but it's getting a little hard. Fortunately, you can get the gist of it by thinking about things that have only two reliably distinguishable states, and I'm going to illustrate the directions by the position of my arm. And the things that show this most clearly, and though they're often talked about as qubits now, but the most intuitively viewable form of qubits are polarized photons. So a photon can have a polarization that's in any direction, perpendicular direction of propagation, and it has some properties. That is, you can't measure the photon's polarization exactly if you just have one. You can't clone it, and you can use these polarized photons to carry information. So, for example, you can say, if I want to, where's that? Can you see even that? I don't even see that. Do you see that? Yeah. Okay. You can. This device will separate horizontal ones from vertical ones, but if you put in photons that are polarized in an intermediate direction, instead of being deviated by an intermediate amount, they behave randomly. So measuring photons along any other axis causes them to behave randomly and forget their original polarization. And so this means that you can, if you know they're vertical or horizontal, you can use each photon to carry a bit. And if you know they're left diagonal and right diagonal, you can use each photon to carry a bit and then just rotate your measuring apparatus. But no measurement can distinguish all four kinds. And this is not a limitation of particular measuring apparatuses. This is a fundamental consequence of the superposition. And this gives rise to the possibility for, well, first I'm going to say that's a little this is something that puzzled Einstein a lot. How, if you prepare something identically, how come it behaves randomly? There must have been something about it when you prepared it that was different to cause it to behave differently. It's like if you go to a hospital full of sick people, some of them are going to die tomorrow and some of them aren't. But the ones who die were sicker already. But if you take a piece of radioactive material, the atoms that are going to decay tomorrow are not any sicker than ones that aren't going to decay tomorrow, and the photons that go into one beam are not any different from that goes to the other. Well, now, my colleague Bill Wooders from Williams College has a nice pedagogic analogy of how this quantum unpredictability. He says it's like the old-fashioned kind of school where the teacher is not, the students are not expected to talk to the teacher other than listening and learning. And the teacher asks questions. So the teacher says, are you vertical or horizontal? And the photon says, oh, I'm polarized at about 55 degrees. I believe I asked you a question. Are you vertical or horizontal? No, horizontal, sir. Did you ever have any other polarization? No, sir, I was always horizontal. So that's how they behave. Now I'm going to tell you why they behave that way. Now, going back to this early history, my college classmate, Stephen Wiesner, who died a couple of years ago, was a grad student at Columbia University, and he noticed, really, I think for the first time, that these quantum effects could do things that are qualitatively potentially useful and not describable under Shannon's theory. And that there's two that he described in 1968, combining two classical messages into a form from which the receiver could receive either one, but not both. And the other thing that he proposed was making banknotes that are physically impossible to counterfeit. And he submitted this paper to IEEE IT, but he didn't pursue it much, and he went off and did other things, except he told me about it, and I thought it was really great, and I kept telling everybody else about it. And eventually, and also in 1970, he tried to improve this idea in his first paper. Well, I'll get into that a little bit later. But here's quantum money. It's a very simple idea. It's impractical currently because you want to you want to keep 20 qubits of one of these 4 states, and the bank knows in which state it's recorded. And the point is that if the bank can check all those polarizations and turn out that find that they'd come out right, but a counterfeiter spoils some of them by trying to measure it. And this is what led to quantum key distribution. When I started talking about it with Gilles Brassard, and he was the first computer scientist who thought these ideas were as exciting as I did. And we worked with Wiesner a little bit on this, but Wiesner was not interested in cryptographic applications because he thought the whole field would get classified and it would be quite unpleasant. But that turned out it didn't happen. Anyway, now, I told you about this conference. Now, at that conference, Feynman urged people to rebuild Turing's theory of computation on quantum foundations. And this idea also occurred to David Deutsch at Oxford University, who was not at the conference. Here's a view of the conference. There's some of these people are, a lot of them are still alive and continue to achieve other things. But this quantum key distribution is a Cold War kind of idea. The good guys trust each other and know who they are, and they don't trust their adversary, and there's more of them than their adversary. But nowadays, especially in the business world, the good guys don't trust each other, and you'd like a kind of cryptography that works where you have to deal with somebody who don't trust each other. And then the idea is you want the 2 guys to be able to negotiate. Suppose they want to, suppose these are 2 people who are considering getting married, and they don't want to tell everything about each other because it might, it might spoil the deal. And they must cooperate. And so the normal way to do this is to go to a marriage broker and explain the situation, and the marriage broker then tells you whether to get married or not. But in the business world, they don't trust, no one trusts an trusted intermediary enough to do that. So what do? Well, this is the other invention that Wiesner found, combining 2 messages into a form that when you read it to get one, you spoil the chance of getting the other. Now, this idea was independently discovered and published, unlike Wiesner, because he hadn't published it yet. And it turned out to be an important cryptographic primitive that can allow this kind of discrete EET, discrete decision-making to be done without a trusted intermediary. It's very important. It was called oblivious transfer. And Wiesner found a quantum way of doing it. And then, even in his original paper, hinted that it was fundamentally insecure. That is, it's insecure against somebody with a very good quantum computer, or he didn't put it that way, very good quantum measuring apparatus. Insecure in principle, but secure in practice. And this was recently shown conversely, that if neither negotiating party can store quantum information, techniques related to this multiplex provide a way of achieving provably secure 2-party negotiation. Of course, the most fascinating thing about quantum information is entanglement. And this is the thing that creates the most confusion and misunderstanding, especially beginning with Einstein, who didn't like quantum mechanics. And he famously called, well, his 2 famous things that he said about quantum mechanics that he didn't like was that he didn't like the idea that God played dice by allowing identically prepared particles to behave differently. And he also didn't like spooky action at a distance, which is what entanglement appeared to be. There are various approaches to that, called interpretations of quantum mechanics, or the shut up and calculate interpretation. But I'll just say about where it comes from, and a kind of way of making it seem comfortable and not unreasonable. And if Einstein were alive, he would probably get used to this idea now and would regret that he said either of those two things. But we don't know, because it didn't happen in our branch of the wave function. Oh, excuse me. Well, anyway, so any processing of quantum data can be done. This is a similarity to classical information processing that wasn't really appreciated. Suppose you have these input lines, these wires, I call them wires. Can anybody, yeah, there. And just in a classical computer, they go through, either they just go straight through or they get operated on by gates, and the gates only need to work on them 1 and 2 at a time. And here's one of the most important gates. It's called the controlled NOT gate. And that is, if we call a vertical photon a 1 and a horizontal photon a 0, if the control photon, I can hardly see that damn thing. Anyway, if the control photon is a 1, the other one is rotated 90 degrees. If it's a 0, it's left the same. And if you give it a superposition of inputs, it gives a superposition of outputs. Because it's a quantum device, it follows the superposition principle. And that means you get a superposition. If you give it this diagonal photon coming in, and you start with the horizontal one on the bottom, you get a superposition between both horizontal and both vertical, which is an entangled state. And this entangled state behaves in ways that can't be explained by supposing that each photon has a polarization of its own. And if you do the math, which is just very elementary high school math, this turns out to be superposition to both vertical and both horizontal, the same as superposition to both left diagonal and both right diagonal, and is not equal to them, both of them being diagonal. So it can be said, if you want to say it at a cocktail party, a state of sameness of polarization, even though neither one has a polarization. So the generalization in going from the sheer theory of Shannon and Turing to the theory of quantum information processing, which we have now, is not only potentially more useful, but is much more beautiful and elegant than the old theory, in the same way that the theory of complex numbers is more elegant and beautiful and encompasses the whole theory of ordinary real numbers. Anyway, a classical bit is just a quantum bit which happens to be in one of two standard arbitrarily chosen states, which we call 0 and 1. Classical wire is a quantum channel that conducts those faithfully but randomizes superposition. And it randomizes them for a reason, because it interacts with an environment. And so when we pass a classical channel is a quantum channel with an eavesdropper, and a classical computer is a quantum computer handicapped by eavesdroppers on all its wires. So people shouldn't be talking about why is there quantum speed up. They should ask why there is classical slowdown. In other words, why are there some calculations which, if somebody is looking over your back while you're doing them, you can't do them as well? That's the question we should be asking. Now, this can be explained by a property that I think I was responsible for this name. It's called a phenomenon called the monogamy of entanglement. And this is certainly an analogy, but a fruitful one to human relations. If A and B are maximally entangled with each other, they can't be entangled with anyone else. And if one member of the entangled pair tries to share the entanglement with a third party, the pairwise relation is reduced to mere correlated randomness. Or as they say, 2 is a couple and 3 is a crowd. So let's take Alice and Bob here, who have become entangled by having this controlled knot interaction. And this means that they are correlated along any axis of measurement. If you measure Alice, you'll find out what Bob would respond to the same measurement. You'll know the state of Bob. And suppose that Bob likes this and he says, well, I'm going to get entangled with somebody else here, so we do that. And then at this point, we end up with this kind of situation where Bob shares only correlated classical randomness with Alice and also with Judy. And if one of Bob's girlfriends leaves, he will find his relationship to the other reduced to mere correlated randomness. But if they both stick around, he ends up perfectly correlated, perfectly entangled, not with either one, but with the now non-trivial relationship between them, an appropriate punishment, which was explored by Colette in this book, which came out right around the time of quantum mechanics, although I believe she was unfamiliar with it. So where does this quantum randomness come from? So I kind of lied to you about this when I said these photons go into that crystal and they randomly go into the top path and become horizontal, or the bottom path and become vertical. Well, what really happens is that they go into a superposition of being horizontal in the top path and vertical in the bottom path. And only when you measure them and detect that the photon is in the top path, then it will also turn out to be vertical. Well, suppose you don't measure them. In fact, if no one observes their behavior, you don't, Bohr would say you can't call it behavior, or as our late colleague in teleportation said, this is Asher Perez, he said, unperformed experiments have no outcomes. Well, anyway, so if you put this, before you combine these two beams, if you put a half wave plate there, which rotates vertical photons to horizontal and vice versa, the two beams will go back together and they'll recover the original polarization. Now, putting that in terms of Bill Wooter's analogy, it's the public embarrassment of the pupil in front of his whole class that makes him forget his original polarization. So if he could undo that awkward answer to the professor's question, and all of the other students and any air molecules that might have heard his answer could forget what he said, he would get his polarization back. So entanglement is ubiquitous. Almost every interaction between two systems causes entanglement, and yet it wasn't discovered until the 20th century. And the reason it wasn't discovered is because of monogamy. Most systems in nature, other than little ones like photons, interact so strongly with their environment that they become entangled with it almost immediately. And this destroys any previous entanglement that might have existed between parts of the system and changes it to mere correlated randomness. Well, of course, everybody is excited about building a quantum computer, mainly because it could speed up some computations, and there may be other ones that we don't know that it could help, and there's therefore a tremendous amount of research going on. This is the most famous type of computation accelerated by a quantum computer. This is showing that using Shor's algorithm. This number over here could be factored in as a product of these two numbers. Now, it's a really hard computation to do in this direction, but if you had a quiet weekend, you could multiply this number by that number. So you multiply the 3 by the 7, and you get 21, and that's where this 1 from over here comes from. And you carry the 2, and nobody's looking over your shoulder. You can do it without a computer, but with a computer, it's very hard on a classical computer, but it would be easy for a quantum computer. So aside from their applications to communication and computation, and really, the word, we don't use it much in English, but it's a better word, informatics, the science of communication and computation together. Quantum information science has already improved precision measurement and timekeeping. And I would say most excitingly, it has provided tantalizing hints about some of the deepest mysteries in physics, such as the black hole information problem and quantum gravity and the origin of space-time. Here is a speech given by John Preskill, who knows far more about those things than I do. But I want to make a remark again about basic science and the importance of it. Most people are interested in what science can do to solve what they consider their most pressing problems. But scientific progress is mostly incremental. Breakthroughs are overrated. And the most important applications of a scientific discovery are hardly ever the ones that people think of first. And in fact, it's likely to be even maybe there'll be 100 years after the thing was discovered. Think about radio. the cumbersome equipment that was used to send telegraph messages across the Pacific. It was obviously a great and important idea in the Atlantic Oceans by Marconi in the early 20th century. But Marconi would not have thought that I have a thing in my pocket that sends radio messages to my wristwatch. And so when anybody tries to telephone me, I have to figure out whether I'm going to answer my watch or my phone. Anyway, so this is, I'm preaching to the choir, or at least some of you out there are the choir. It's most important to keep steadily supporting science, and mostly don't worry about the applications of it. And even in applied sciences, ideas go through ups and downs on a scale that's sometimes longer than a human lifetime. For example, around the time I was in kindergarten, people were talking about computers that recently discovered. They called them electronic brains. And they said they'll soon solve problems such as language translation and will revolutionize the world. Of course, they did revolutionize the world, but they didn't solve the problem of language translation until around the time that, that I met my wife, and we spoke different languages, but we were sitting there talking to each other through Google Translate. Anyway, but that was about 60 years later. More than that, 70 years later, something like that, yes. Anyway, artificial intelligence is very hot today, but it went through a long dormancy. So this is just that. So I would say it's important to work on these toy problems. And I think, except for people who have a irrational conviction that quantum computers will never work, it's not very important to just show that you've done something that a classical computer can't simulate, if it's not an important, useful thing. The important thing is just to keep improving the quantum computers until they can do some of these things that are worthwhile. And anyway, they may never be the biggest part of the information revolution, but they're such an important part of the way things are that everybody should understand them. In fact, I say, where we go? So wait, was one. Yeah, it's like the roundness of the Earth, or basic understanding of what black holes are. Every educated person should have that, understand the gist of quantum information. And if, just to be a well-educated person, I think Einstein probably stood in the way. Most people think that quantum mechanics is too hard to understand. It's much worse than rocket science, but that's not true. And if you want to get a longer version of my talk, there it is up there. And if you want to find out more about this very unusual person, Stephen Wiesner, who had some of these ideas so long ago, you can look here. Okay, I'm done now, I think. Take any questions. How does this work? Where did my chair go? Yes.
Right, thank you very much for really interesting talk and for your insight. Maybe we could have like one quick question from audience. Yes, please go ahead.
Thanks, great talk. I'm going to ask a pretty obscure history question. So you talked about Deutsch and yourself and a couple of the others in the early 1980s and the work you were doing. What about Paul Benioff's work on quantum Turing machines? How would you place that in the?
Oh yeah, I knew him well. He said, of course, that we believe the universe is fundamentally quantum mechanical. And so therefore, the idea that the universe can perform a computation it's not been made rigorously demonstrated unless we can show a quantum system can perform computation. So he tried to show that a quantum system describable by a Hamiltonian could perform classical computations. And that was his big result. He remained interested in the field. I think he may still be alive, but that was what his approach to it was.
Thanks.
Right. I'm pretty sure many people has more questions, but I think it'd be better if we take the questions to the break. Let's thank Charles Bennett again. Thank you very much.
Well, thank you.
Now I would like to introduce our second speaker. Again, it is my great honor to introduce Professor Rodney Van Meter from Keio University and also from Keio Quantum Computing Center. And he will tell us about networks for modular quantum systems. Please join me in welcoming Professor Rodney Van Meter.
Hi, good. Oh, good, we have it on. All right, so welcome, and thank you all for the invitation. I'm very happy to be here. I'm not going to talk extensively about the connections between Yonsei and Keio University, which is in Tokyo, or in the Tokyo area, because if I were to start talking about that, I'd be here all afternoon just covering that. This morning I was searching up the actual documents about the relationships between Keio and Yonsei and discovered that there are 14 separate agreements that actually cover our interactions. So Keio and Yonsei have a long history together, and we're thrilled to be part of this, including particularly this trilateral connection with Yonsei and with National Taiwan University on quantum computing. So my background is in engineering. I am a computer engineer or a computer architect. I'm not a quantum physicist, and I'm not a computer science theorist. My background is in storage and networking and architecture and operating systems and things like that. But I've been working on quantum computing now for 22 years as of this month. So I want to show you a little bit about a particular result that's the result of our current active work, rather than going into sort of a really broad high-level description of the sets of things that we're doing at the Keio Quantum Computing Center, or even of my own research and career. I want to focus on one particular thing, and that's networks for modular quantum systems. So we're going to talk about some of these sorts of things, which you'll see coming up shortly. So this is just a list of some of the titles and organizations that I'm involved with, which we don't need to go into. But I really do need to point out that this is collaborative work, this is not just my work, but this is just the list of the people who have worked on the quantum networking projects with me, not including the quantum computing projects, although there's a lot of overlap in them. So this is a photo of my group from last fall. This is only about 2/3 of us. There are about 40 of us now, from first-year undergraduate students up through postdocs and research staff and other faculty. And that's one of the unique things about our system, is that in our system at my campus, the undergraduates, usually in their second year, join our research group and do marvelous things. So in fact, some of the results are actually supported by and even developed by some of our undergraduates. We also have this organization that's known as the Quantum Internet Task Force, which you may check out. This photo is from when the QITF was actually founded. I wasn't there because that was actually held the day that my sister was getting married in the United States. And every once in a while, I do succeed in putting my family above my work. So I also want to point out that I am editor-in-chief of IEEE Transactions on Quantum Engineering. And in particular, the reason I moved this from where I usually have it at the end of the talk to up here is because one of our relationships between Keio and Yonsei, although that's not formally part of the university relationship, is that Professor Jong-Gil Ko from here at Yonsei is one of the editors on my journal. And I would encourage you to read, submit, and review for us. And I'm also always on the lookout for potential candidates for new associate editors in the journal. So, very roughly speaking, this is a roadmap of sort of where we have been in quantum communications over the last 4 decades and where we're going. And in the upper portion of this, we have, broadly speaking, quantum key distribution. In the lower portion, we have entangled networks. Those are roughly 2 classes of networks that have been developed around the idea of quantum communication. And my own research focuses primarily on the entangled networks here at the bottom, so that's where I am. But you can see this guy, Charlie Bennett, was critical in the early evolution of the quantum key distribution networks, and our other keynote speaker, Richard Joza, collaborated with Charlie on the first paper on quantum teleportation, which is the key element in entangled quantum networks. And then this is Wolfgang Duhr, who wrote one of the first papers on what are called quantum repeaters, which is a technique for building shared entanglement among systems across a distance. So this is sort of roughly where we are, and I hope that we will get to a commercial quantum internet sometime in the 2030s. But today I don't want to talk about the wide area networking. Instead, I want to talk about essentially data center sized networks, and that's the networks for modular systems. So this is a photo of El Capitan, which is the largest supercomputer in the world these days. And we want to get from here to here. Well, I want to put together a relationship between these 2 things. Okay. So that's what we're going to cover over the next 25 minutes or so. Let's take a very rough look at the necessary roadmap for quantum computer architecture. And this, hopefully, will help us motivate why data center scale networks are actually necessary. One of the key elements in quantum systems that we understand is that in order to have the actual computational advantage that we're trying to achieve, you need to have entanglement that stretches essentially across the entire machine. And one of the seminal papers on this particular area is this one by, again, by Richard Joza. So, where are we? Well, on this horizontal axis here, which says more application qubits. We would like to have a large number of qubits available and actually to order execute quantum algorithms, but we need for them to be high fidelity. So somewhere down here in the early days, going back to the 90s, there were early qubit demonstrations, and today we are in what's called the NISQ era, or the noisy intermediate scale quantum systems. And ultimately we want to get to somewhere up here in the upper right. So this is essentially where we are today. The very first demonstrations of fault tolerance or the effective error correction can be said to have been demonstrated over the last year and a half. Other people, of course, are doing their best to reduce the amount of noise in current systems, or they're building systems with more qubits but not necessarily better improvements. And ultimately, we want to get up into this direction where we increase the code distance, which means to use stronger and stronger quantum error correction. And ultimately, we want to add more fault-tolerant qubits. This will carry us to what I call max SQ, the max single-chip fault-tolerant quantum system. Now, how big that's going to be, what kind of system that's going to be, is going to vary depending on the technology that you've got. In the case of superconducting systems, it may be hundreds or low thousands of physical qubits. And then the question is, how good is your error correction and how large a system does that actually bring? Once you cross that threshold or hit that limit, then after that you're going to have some form of interconnect that actually allows you to connect multiple smaller computers together to build larger systems. And this principle can be applied in this era of NISQ systems, but where we really want to get to is we want to get to a fault-tolerant quantum multi-computer. So that's where we're headed in terms of this talk. So let me give you just a little bit of a history of this, and even this is sort of relatively selective. This is not a full history of everything that's gone on. As far as I am aware, of course, the idea of using multiple quantum computers together to solve one larger problem that a single system can solve, that idea is fairly straightforward. But the first actual proposal to do that, of which I can recall or I am aware, it was by Yonsei Kim, who had just moved from AT&T Research to Duke University in 2005. So he proposed a system with a group of nodes, this is here in the lower left here, connected via an optical interconnect. Each one of the nodes would hold multiple logical qubits, and there would be some sort of crossbar system that connected it all together. Well, around the same time, I was actually working on my PhD thesis at KO, and I started working from the top down, trying to figure out if you're going to execute some sort of quantum algorithm, how big does your system need to be? How good does it need to be? How fast does it need to be? Then applying some of the basic principles from classical computer architecture, trying to figure out, okay, what can we do? One of the outcomes of that was that, in fact, although you might think you might want some sort of complicated network connecting things, in fact, if you just connect a set of nodes in a line, it actually works pretty well. Other work that was going on at the same time was in Melbourne. This is Daniel Oy and Simon Devitt and Liang Zhang at Harvard. And later, various groups of us actually collaborated. This later proposal here, 2010. Arguably, this paper actually had sort of a negative impact on the field. I think it actually drove a couple of people out of the field because we did sort of a rough analysis for a particular hardware implementation using quantum dots with rather extreme amounts of loss in the system and fairly low fidelity, and we came up with, well, you're going to need a system that's going to have 6 billion quantum dots in it. Some of the other physicists went, whoa, wait a minute, I don't have any idea how to build a system with 6 billion quantum dots in it, and so they sort of shifted direction and went in other ways, I think. Not long after that, the group of Simon Benjamin at Oxford proposed that you could actually use very small nodes and execute the surface code form of quantum error correction between sets of smaller nodes, which is actually sort of echoes what Liang Zhang had actually done, except for a different code back at Harvard in 2006. And then later, I worked with a group at Yonsei Kim's group at Duke University on a tree-structured based system that was the PhD thesis of one of his students there. That carries us roughly, covers sort of a decade, from 2005 to 2015, give or take. Then after that, there was rather a lull. For about 6 or 8 years, people were focusing on NISQ systems and small-scale systems, and there wasn't really a lot of work on these modular systems at that time. But starting about 3 years ago, it sort of started to resurface, and a series of papers started to really reappear, and you'll see, whoops, hang on, let's see. A set of things here in 2023 and 2024. Some excellent work from Spain on how to actually apply or how to distribute applications to networks and what that's going to do to the traffic on the network. Some work from MIT. Internode lattice surgery. Again, this comes from whoops, let's see. That says Melbourne, but I think that's actually Sydney. Oops, sorry, my fault. And then Arquin is, Arquin or Arquin or Arquin, I don't know, I call this paper Ang and the Golden All-Stars because the first author, his name is Ang, but it's got everybody in the world on it. It's got Sophia Economou, Ike Chuang, Andre Faraon, a bunch of great people on it. And then our own work on the Q-fly, and that's the main thing I want to talk about here, which derives from a dragonfly network. So if we're going to design a system, there are a whole bunch of questions we need to address. And like I said, me being a systems architect, I like to start from that view at the top level. What is it the system's actually going to have to do? And so we have to cover sort of this whole range of questions about how we're going to put the system together. I want to start by telling you first just a little bit about a couple of these questions. The quantum error correction construction, how do we map logical qubits onto the set of physical hardware we've got, and then also ultimately the method for actually executing those logical gates between nodes. So this is not the first paper to propose the execution of remote gates, but this is what I consider to be the standard approach these days. From Jens Eisert and company in 2000, they actually showed how to execute a C0 gate using an entangled bell pair here. This squiggly line here between A1 and B1, that's an entangled bell pair. And of course, these remote gates are actually ultimately related to or build upon the techniques from teleportation itself. Now, in terms of the error correction, you have two main options. One is that you can confine a single logical qubit to one node, or you can have a larger code word that actually spans across multiple nodes. Now, in this first case, you could be working with something like Steen code, or you could be doing the surface code with lattice surgery inside of things, as opposed to some of those earlier designs where we actually talked about 2D surface codes that actually span across multiple nodes, which actually is possible, but actually has some significant drawbacks. All right, so let's talk about the traffic pattern. And by that, yes, I actually mean whether or not you're getting in a car and trying to go from here to Seoul is actually going to be sort of a nightmare, or whether it's going to go smoothly. The same kinds of issues of traffic, when we talk about that in networks, we're talking about how much are people actually using the system. So let's take a look. Let's say we have 4 quantum computers, and they are connected via some sort of network, which I've drawn here as a cloud. And that cloud, and we'll talk more about the structure of that later. But what we want to know is we want to know what the utilization of that cloud is actually going to be. Well, let's say that the application that you are actually trying to execute has initially sort of this loop structure. So this first round of communication, these 2 nodes are communicating, these 2 nodes are communicating, these 2 and these 2. All right, round 1 of communication. Then maybe round 2 of communication, actually the ones diagonally opposite want to communicate with each other. And then maybe in round 3 it returns to that. So when we talk about that traffic pattern, that's what we mean. Now, how does that actually work in practice? Well, this circuit is actually an addition circuit. This is based on the addition circuit created by Vedral, Barenko, and Eckert. And in this, we actually looked at the 2 possible approaches here, which I called telegate and teledata. So telegate is the one I just showed you, where we use that bell pair to actually execute a gate between 2 qubits that are far apart by consuming that entanglement. And in that case, this would be those blue circles. So if we split here between node B and node C, we've got this blue dashed line here. Assume that's where we have split the qubits between 2 nodes. Well, that would mean right here we have one gate that we need to split, here we have another gate we need to split, and here we have another. So that's going to require 3 places where we actually execute or actually consume entanglement to do the long distance gates. Alternatively, we can do what I call the teledata approach, marked in the red circles here between nodes A and B, where you'll notice this line here takes a jog and it goes up. In this case, we might take one of the qubits and teleport it to the other node. And then once you've got it at the other node, then you can use it as many times as you want at that node before teleporting it back. So you've got 2 choices, telegate and teledata. All right, so this brings us to the bits on network topology. So network topology, let's go into this and take a look at this. Whoops, the animation seems to have failed here, sadly. Sadly, it grows kind of nicely. In this case, we've got each node with 4 interfaces, north, east, south, and west. So if you want to connect a set of nodes into a larger system, this is one approach. This is what you would call a 2D fabric or a 2D mesh. This is actually much like a lot of the classical supercomputers that were actually built initially in the 1980s and 90s, including things like the Intel Delta Touchstone and things like that, where you just connect them up in this big array, and then you communicate by sending data from one node to another node to another node. Right? Well, this might seem sort of attractive even for building a large-scale quantum computer, but one of the issues with this is this. In this particular case, So you've got these channels, and at this level, we've just drawn sort of an abstract channel here. We're going to use it for something. But if you want to actually build a physical system, there are different approaches to actually creating that shared entanglement between these nodes. But one common approach uses a device that sits in the middle of this network, or sorry, in the middle of each one of these links, and that device is called a Bell state analyzer. So if you want to have a network with a lot of nodes, you're going to wind up with a network with a lot of Bell state analyzers in it. These are, generally speaking, separate devices from the quantum nodes themselves. This, in fact, in our lab, is what one of these Bell state analyzers looks like. Inside this little cryostat here, there is a device known as an SNSPD, a superconducting nanowire single photon detector, and it's taken me 2 years to learn how to say that without stumbling. So all of this equipment that you see here, all of this is required in order to do this. And what it does is this device takes in 2 photons, and when those 2 photons match up properly, what we get is we get entanglement between the 2 sources of those 2 photons. So that's what a Bell state analyzer is. And as I said, we've got one on each one of these links. So you're going to have one of these devices for every single one of those links. That's starting to look like a lot of equipment. But there's one piece of good news here, and that piece of good news is that, in fact, what's inside here is not just one Bell state analyzer, but enough detectors to actually be a set of Bell state analyzers. And so if we can put more of those inside one single one of these doers here, then we can have a somewhat different architectural structure. So we can do this kind of structure. This is the actual approach being taken by Chris Monroe and Jungsang Kim and their company IonQ. Modulo some differences about what's possibly here in the middle. But on the left, you have a set of quantum computing nodes, and then on the right, you have a pool of Bell state analyzers. And in the middle, you have some device that takes photons from here and routes them there, and it gives you something like this. If you want to create entanglement between this node and this node, you route a photon from here and a photon from here, and they arrive at the Bell state analyzer, and they get measured together. When that happens, when that succeeds, then you are left with entanglement between this node down here and this node up here. Now, if you've designed your system properly, if you've done a pretty good job of it, you might actually be able to do not just one of those at a time, but 2 of those at a time, and potentially all pairings of this. And designing the system that does that is one of our key design problems. One approach we have taken to doing this is a layout for a chip like that would actually support a large number of possible inputs here on the left and slightly more abstracted symbol for the Bell state analyzers here on the right. On the left there, if we amplify that, here's a simple example. So normally when you are building interconnect networks for supercomputers, you need to be able to send messages from every node to every node. For this quantum system, we don't need to do that. What we need to be able to do is we need to be able to pair up signals coming from each of these nodes, but we don't care where they get paired. So in this case, we've got 4 inputs, and these 2 boxes are switches, but right now they're just set to let the signals pass through. So this pairs the 2 input signals 0 and 1, and this pairs the 2 signals 2 and 3. If we set the second switch, now we have pairs 0 and 2 and 1 and 3. And if we set both switches, now we have pairs 1, 2, and 0, 3. And this has covered all of our combinatoric options for this particular set of things. And if we do this, we scale this up into a system like this. This is one of several designs we have proposed. In fact, what we find is that by paying attention to this pairing problem rather than the all-to-all communication problem, we can actually reduce the amount of resources that are required by about a factor of 2, which can result in a dramatic reduction in the loss of those individual photons and a significant improvement in the performance of our system overall. So this was a paper that was published in IEEE Quantum Week in 2024. Yes, 2024. And the work for this, the lead author on this, Koyama, she's one of my undergrads in my group. So again, this brings us back to the El Capitan. Nice little computer there. This little computer has a network like this inside of it. This network is known as a dragonfly. So this is the classical dragonfly network, which was, the concept of the dragonfly was actually developed in the group of Bill Daly, who is now chief scientist at NVIDIA, and he was a grad student under the same professor that I was an undergrad under at Caltech in the 1980s. So this structure, you have groups here. You have groups of nodes and groups of switches. The little pink dots are the computing nodes. These orange boxes are switches. And so this is one group, and then there's a connection across here to another group. And then between each of these groups, there's a set of connections. So this sort of two-tier structure. This is commonly adapted in these kinds of large-scale quantum computers these days. I think, or sorry, large-scale classical supercomputers these days. I think 8 of the 10 largest supercomputers in the world today actually use some variant of the Dragonfly. So the basic idea of a group, when we extend this from the classical world into the quantum world, we've got some set of N nodes over here that can emit photons, and maybe they are quantum computers or some sort of sensing device or something. And then again over here on the right, we have a cryostat with a set of Bell state analyzers, and in the middle we have some sort of switching network. And this switching network might be that chip that we were just talking about a minute ago. In addition, we have not only the set of inputs coming from the nodes here on our local machine, we also have a set of inputs coming from other switches and a set of outputs going to other switches. And so this structure has the ability to actually scale to very large numbers. So, final question. Can we build this? Well, the answer is we started. Both with actual experimental work at small scale and at larger scale simulation work. And in November 2022, this is what our lab looked like. After quite a bit of hard work by people, including some of our undergrads and many of those members that you saw before, in November 2024, it looks more like this. So we got a bunch of stuff here in the lab now, and things are actually working. So, what's working? This is a small-scale view of the quantum dragonfly, which we call the Q-fly. And the part actually in pink is actually up and running in our network. Excuse me. The set of nodes that are in the system, we have node A, node B, and node C, and a set of switches that connect us to a Bell state analyzer there on the back. And this work can actually scale to a larger set of nodes and a larger group here. Now, what we're doing today is we're generating single photons, and these single photons are generated here. This device is an entangled photon pair source here. We're generating those and measuring one qubit here, and the other gets sent to the Bell state analyzer where it gets measured. There is no computation yet in this network, and there are no computational nodes yet in this network, but the goal over time is to replace these individual nodes with computational nodes, probably starting first with ion trap nodes, which have the advantage that they actually spit out photons that we can put into an optical fiber and use there. If you scale it up, you get something that starts to look like this. This is still relatively small for a supercomputer-sized thing, but it's a diagram that actually still fits on the screen. And again, we can do local communication within each group, or we can do communication between nodes in other groups, and potentially we can actually parallelize some of this. But what's interesting and what matters in all of this ultimately is the number of switches the photons have to cross, because that's where we actually have the potential to lose quite a significant number of the photons. So here, both photons, each photon crosses a switch once, so our cost is 2. For the green pair here, this crosses 1 switch, 2 switches, and then 3 switches. And then for the red path, it crosses 1, 2, 3, and 4 switches. And so that assigning communication traffic to those different paths is one of the important things that has to be done. Now this is the actual experimental output, the actual experimental result here. We generate Bell pairs or photon pairs with a fidelity of 94% here at node A, and also with 94% here at node B. And then after actually passing them through the switching equipment and through various other pieces of equipment and to the Bell state analyzer, we have end-to-end entanglement across 2 hops, and the entanglement for that is currently about 64%. And this diagram up here in the upper right shows you that, in fact, our photons, we are getting the correct kind of interference between the pairs of photons we're creating. And the photons themselves are, I think they're on the order of, I think they're about 1.5 millimeters long, if I remember right. It's written in the paper somewhere. All right, so this takes us to an analysis that looks something like this. We analyze the system based on the total number of detectors and ultimately, of course, the total execution time of individual algorithms, where this rather complex looking diagram here is the mapping of the quantum Fourier transform onto a set of 4 nodes. And there are different configurations with different numbers of logical qubits in each node, different configurations for the switching, and you can find the details on sort of what kinds of configurations we think are likely to work well in the paper itself. This paper is actually available on the archive, so you can get it from there if you wish. It's currently under review. We hope to get a result on it within a couple of weeks. And I would say that that has connected our supercomputing system to our quantum computing system here. And we think that we have answered all of these questions in the affirmative with reasonable first cut answers, but there's always a next generation of everything. And then some couple of final comments here in my last minute or so. RFCs are the documents that define how the classical internet works. I am the chair of the Quantum Internet Research Group, which is part of the Internet Research Task Force. And 2 years ago now, already, we published the first RFC that actually describes the behavior of quantum networks. And we have an online course. This is Mikhail Hajdushek, who is a project associate professor in my group. We have a set of online courses on the fundamentals of quantum communications up through quantum internet. And the first one, there is a companion class or a companion textbook that is available that's on the archive, which we are hoping to get published soon. So if any of you would like to have that, you can find that at the QR code. And all of there are additional exercises and things with this course that are only available in the learning management system we have, but the videos are all available on YouTube, so you can find those on YouTube there. And with that, I will end, and I will encourage all of the younger students to actually go quantum native. You'll see I'm wearing my quantum native t-shirt, but I am too old to be quantum native because my definition of quantum native is students who learn classical computing and quantum computing at the same time. And I learned classical computing first, so I can't be quantum native. But the students sitting here and elsewhere, I think you all can. And with that, thank you all for your attention. And by the way, yes, I took this picture. I'm kind of proud of that one.
Right, thank you so much for a great talk. I think we should move forward to the next talk. So I'm sure many of you have many questions to Rodney, but please catch him during the break and talk to him during the break. Let's thank Rodney again. Right, so our next speaker, the last speaker of this session is Professor Junwoo Bae from KAIST, Korea Advanced Institute of Science and Technology. And he will tell us about building and exploring quantum networks. Let's welcome Professor Junwoo.
Hello, good afternoon. Thanks for introduction, and so thank you for inviting me here. I'm happy to share my idea about quantum information theories of quantum network and our directions and the recent research. So the title I put here is Building and Exploiting Quantum Networks, and I'm Junwoo Bae from School of Electrical Engineering, KAIST. And I will start with introduction about entanglement and quantum networks, and then I will talk about our recent research, how to deal with the noise in quantum network, and then I will come to some certain applications. So this morning when I was finalizing my slides, I was thinking, so what is the good way of, or practical way of introducing quantum networks? I Googled I typed quantum network in Google, and AI already provided this solution. So this quantum entanglement and teleportation and quantum cryptography and so on and so on. Okay, so then quantum internet, the term coined, or term appeared in this paper. So it's not a real research article, but it provides a vision for the road ahead. And this paper was leveraged, I would say, by this work, solid-state quantum memories by MB Center. So here they realized entanglement distillation in solid-state quantum devices. But this is not the first time about quantum internet. So about 10 years before this work, there was another quantum, well, actually the first paper that mentioned quantum internet was by Jeff Kimball. That time, this paper all about atom-photon interactions. So quantum repeaters and long-distance quantum communication and quantum repeaters, how photon state can be stored in atomic ensembles and so on and so on. And why? These are the basics of, or basis for quantum internet. Then again, like 10 years back, there's a paper by, so one by Charlie Bennett here, and the other by Rich Josa, also here. So both are about entanglement distillation. So nowadays we call entanglement distillation, and the first paper called purification of noisy entanglement. And for faithful quantum teleportation. And the second, they share more or less a similar idea as a quantum privacy amplification and security of quantum cryptography over noisy channels. But let me tell you what they are, okay? So actually, this is the two papers I want to celebrate for quantum networks here. Okay, so this is entangled state. We call entangled bit. So it's a unit of entanglement. And it's a very natural process that both of them, or each of them, they interact with the environment and they became a noisy state here. So it's no longer a pure state, may contain entanglement, but it contains some noise. So here I have a parameter here, f, we call fidelity. F is 1, then we have a noiseless and entangled bit. But f is larger than or smaller than 1, then we have some mixed state and noisy entanglement. And this direction, blue, is a physical process, a natural process. But the other way around is another physical process. There's no way to deterministically transform mixed state to pure state. Then this paper, two papers, one by Charlie Bennett, purification of noise entanglement and so on, and the other one, quantum privacy amplification by Rishi Josa. These two papers address a solution to this problem. So it is not possible to follow the blue direction, but we slightly relax the condition. So transformation can be probabilistic. So we allow the probabilistic transformation. Then we have many copies of noisy entangled states. And out of them, we can have some clean and pure entangled bits. So it's called distillation of entanglement. And so this is possible and specifically shown by a certain protocol. So it's possible. Then the message I want to emphasize here is conceptually. So one can be completely pure out of noise, or one just needs to be noise, to be pure. So we don't need anything pure, but just collecting lots of noisy resources, and then we can extract some clean and pure resources. So yeah, it's quite intriguing. It's very nice, remarkable. And once we have this clean entangled state, entangled bits, and what can we do? And the first option, one of the first options would be quantum computation. So quantum computation can be done by, not just by quantum gate, but also by entangled state. So instead of quantum gate or quantum dynamics, just collecting large size entangled states and just performing local measurement, and we can realize any quantum state transformation, which is quantum computation. So this was proposed by Rasendorf and Hans Brieger. It's called one-way quantum computer, or nowadays we call measurement-based quantum computation. Okay, so entangled state, this pairwise entangled bits can generate useful entangled state for quantum computing. Okay, so then next about quantum communication. So two parties, say often we call Alice and Bob, they want to share this entangled state because these are sharing this maximal entangled state implies, two parties can realize quantum teleportation, so sending one qubit for free to the other in a noiseless manner. And they can also realize a secure quantum communication. Okay, let's do that. It doesn't look very difficult because just 2 photon or 2 qubit scenario. And yeah, so let's do that. Then the physical limitation in this is a loss. So if you use photon, okay, so then photon hardly interact with an environment, but there's a photon loss. So if we call this distance L, okay, and alpha is a parameter that takes into account all the environmental conditions, like optical fiber or atmospheric effect and so on. And then the probability that the photon arrive at this distance L drop down exponentially. So then often the practical limitation about 50 to 100 kilometers. And after that, yeah, maybe we don't get any photons from the other. Then I mean, we do have the same problem in classical communication as well. Then what is the solution for that is signal amplification. But it doesn't work for quantum scenario because no cloning theorem here. So we cannot copy quantum state, then there's a limitation in photon distribution. Then how can you realize long distance quantum communication? And then the solution is this one is called quantum repeaters. So sharing entangled state between different nodes and then performing Bell measurement or teleporting this one to the other or entanglement swapping, all these are synonyms. And by using entanglement, we can extend distance in quantum communication. So that's a great idea. And combining these two, entanglement distillation and quantum repeater, so different nodes, between nodes, okay, and then parties and repeater, they realize entanglement distillation. So each node, they share clean entanglement bit, entanglement bit, entanglement bit, and then once they are sure that, okay, we share entanglement bit, then repeater applies entanglement swapping or Bell measurement or teleportation, and then after all, I mean, two parties far in distance, they can share a useful entanglement state, entanglement bit. Okay, so then in this way we can extend quantum communication and also quantum network as well. Okay, then just look at more carefully about the steps here. So there are two papers, there's one by Charlie Bennett and the other by Rishi Josa, and two papers, they have a different steps a little bit in the local operations, but they share the same operation in common, which is this bilateral CNAT operations. So it means take these two states, okay? So F, and this can be anything, but after Bell diagonalization and twirling and so on, then this can be diagonalized. Okay, at the moment we don't have to care, but starting from this noisy state in the first register and take the second copy here, and Alice and Bob, they perform local operations by using CNAT and perform measurement in the second register. Whenever they got the protocol works as follows. So whenever two parties get the same outcome in the second register, so I equal to J, then they accept the one in the first copy. Otherwise, they discard. So then keep doing that. So once the outcomes in the second register are identical, then we have a desired result. So we have a slightly improved fidelity F prime. Okay. So keep doing that. We can distill entanglement, and we can reach the point up to F equals 1. So this is some scheme. So suppose we are here F, then it goes up like this, and we have a F prime, and then we have a higher value, and then on so on, so on, so on. So therefore, we can reach this maximum value, which is then we reach entanglement distillation. Okay, then let's do that in reality. Then what happened? This operation is of course noisy. Then then it's also one of the difficulties to realize entanglement distillation in practice. Okay, so next part is about how to deal with this noise that happen in entanglement distillation. Actually, the paper by Beaufort Duo and Hans Brigger, Ignacio Cirac, and Peter Zoller, so they looked at the realistic constraint in this entanglement distillation protocol. For instance, measurement in the second copy, like this. Okay, so it detector contains some noise. So state is 0, but it gives sometimes 1 with some probability. Also the other way around as well. So 1, then it gives outcome 0 with sometimes. If this happens, then before entanglement distillation was possible, for F is between 0 and 1. Now, okay, so there's a bound which is larger than 1/2. So we lose the chance of distilling entanglement from weakly entangled state. And moreover, this bound has there's an upper bound. It means we cannot reach F equals 1. So we reach certain entanglement with this limited fidelity here. So measurement error is quite critical in this scenario. Okay, so that was the problem or analysis done in 1999. And okay, so recently we worked on that, and it's 2024. And here we provide how to purify, not entanglement, but purify noisy measurement. So the scenarios are very similar. So before entanglement distillation, we only have a noisy entanglement, and collecting noisy entanglement, we could have a pure and clean entanglement bit. And here we have a noisy detector. So this noisy detector, and noisy detector all the time. And so some states are coming in, and we have use ancilla, and state interact with the ancilla by CNAT gate, and we accept the outcome whenever all the noisy detectors give the same outcome. So all zeros, all ones. Otherwise, we discard. So in this way, once the outcomes are accepted, these converge to clean detector. So we only keep using noisy detector, and after that, out of that, we can distill noiseless quantum detectors. Okay, so that's we know how to purify noise measurement and apply this one to this entanglement distillation protocol. And suppose that error rate is about 10%, which is quite high compared to, given that our current technology, 10% is almost the maximum error rate for detector. Then how many ancillas do we need in practice? The answer is surprisingly just 2 or 1. Okay, so we don't need like 10 ancillas and so on, but just 1 or 2 ancillas. We already get like 0.505, which is close to 1/2. So it's a really very practical solution to noise measurement. And our idea is also conceptually the same line of the first papers about privacy amplification. So it's called also Charlie Bennett, also Ueli Maura, secret agreement by public discussion. So secret is something private to 2 parties, but 2 parties, they keep doing public discussion, which is open to even eavesdropper, but they can distill secret key. So that's the idea of this paper. And also it's related to this one, a generalized private amplification. So all these results are in the same line of conceptual equivalence of entanglement and secrecy. So I'm very happy with this result. And moreover, recent quantum computing or NISQ computing, so computing with a noisy quantum hardware, basically this can be defined as a lack of quantum error correction. So we are not able to perform, quantum circuit in a deep depths, maybe short depths, so that error is not accumulated. So we keep doing short depth quantum circuit, but we keep performing measurement and state preparation. So there will be lots of steps of measurement and state preparation. So therefore, what happens is the measurement error may propagate over different layers. But here, our method of purifying noisy measurement can be applied to this noise, the error of noisy quantum computing, and we can prevent measurement errors from propagating different layers. Okay, this is the second one. And okay, so the third part, let me be quick. So once we have a clean quantum network, then what can you do? The first one, okay, let me slightly change our approach. To see quantum advantages on open network, let me address this question. So how quantum and classical are distinct in information processing? So this is how I see advantages of quantum information processing. So maybe the first one would be Bell theorem. So Bell inequality tells there's some statistics on measurement outcomes of quantum systems, and there's a bound by classical model is 2, and quantum model we can go over that 2 square root of 2, but this is not a limitation dictated by relative causality. So in physics, it's a relative causality dictated even larger bound of 4, and we don't know any system yet to reach this 2 square root 2 and 4, but this doesn't violate any other physical principles. Okay, for that, one can ask an interesting question. So maybe in cryptography, eavesdropper is not quantum, but it's dictated by no signaling principle. It's a relative causality. And still, quantum key distribution can achieve security. So it's by Jonathan Barrett and Hardy and Kent. and also Tonya Sin and Jisan and Masanes quite some time ago. And this is just fundamental question, but this leads to fantastic result in called device independent security of quantum key distribution. Okay, second, also I like to ask the same question about quantum state discrimination. So we have quantum state discrimination. It's a very simple thing. So non-orthogonal state cannot be perfectly discriminated. And this is actually one of the ideas for quantum key distribution also by Charlie Bennett. So two non-orthogonal states can be used for quantum key distribution. Okay, so it's a very simple problem. Take a two states and give an outcome. And then from the detector, one has to guess which one is which. It's a very simple problem. It's a textbook problem. And 2000, okay, and then state discrimination has these two interesting properties. The first one is that in the case of binary equality, there's a gap between quantum and relativity causality. But in state discrimination, there's no gap. So no signal principle can tightly dictate or determine optimal quantum state discrimination. And quantum state discrimination is conceptually also equivalent to no cloning theorem. So if a physical theory contains no cloning of state, whatever is like a generalized probability theory, but then it also implies that the theory should contain no perfect state discrimination, and vice versa. And this is, so I've explained this one in the review. And in 2018, Ralph Specken, he looked at this one, state discrimination, and compare quantum state discrimination with a non-contextual theory, which is kind of classical theory. And there's a gap between non-contextual classical theory and quantum theory in state discrimination. So this gap may be amplified and can be used for certain applications. And we looked at also the same problem, but it's a different scheme of state discrimination, called unambiguous state discrimination, also maximum confidence discrimination. In all the scenarios, we could see the gap between non-contextual theory, which is classical, and quantum theories. And it has certainly applications for random numbers. Yeah. And well, so this is another fundamental result. In a communication primitive, there could be some advantages, in particular random access code. So there's a game, like a guessing game, and at least give some preparation and both make a guess, then we could see some gap between quantum and classical scenarios. And maybe this is the last thing, last quantum advantage I want to emphasize. So it's Peter Shor who gave the first idea about how we can get network advantages in communication. So he went to two sender and two receiver scenario and looked at the channel capacity. So, okay, so then this is the result there, and there's one of the open problem is that, okay, so two parties, they share non-classical correlation, can be quantum or can be post-quantum correlations. And they use this correlation to encode messages. Okay, so then there is some channel such that quantum encoding or post-quantum encoding give higher channel capacity than classical ones. So that's the result here. And so they provide different channels for that. The first channel type 1, post-quantum give advantage over quantum and classical, but there's no gap between quantum and classical. And channel type 2, there's a strict hierarchy of classical and quantum and post-quantum encodings. And then the open problem here is that for this type of channel, can there be a gap between quantum and classical channel capacities? And we have the answer here. So we found many also different kinds of network channels where we can see clearly quantum advantages over classical ones. So once we have a quantum network, I mean, we could have advantages in channel capacities. Okay, so I don't have much time to go through in detail, and it's like some ongoing project in my group. We are working on this quantum computing with the noisy hardwares. So one is ongoing project is this quantum algorithm for protein structure prediction, and the other is birth location optimizer. This is similar to Kubo problems. So connecting them, of course, there must be, we are also looking for some advantages, for instance, distributed quantum computing or scheduling problems and so on. So even, I mean, connecting noisy quantum devices, there might be some advantages. So this is something we are looking for. And okay, so that's the summary. The part 1, I provide general introduction about entanglement and quantum network. And the key I think, the key here is that certification of entanglement is very important. So therefore, we need actually classical outcome or classical message for quantum properties. So basically, from measurement outcome, we want to be sure that there is entanglement. And the second, we provide how to purify noise measurement to enable entanglement distillation with the noisy detectors. And this also can be used for quantum computing. And again, although there's error correction and so on, but I believe, also in my opinion, we need more tools to deal with quantum errors to reach the point we want to have, for instance, quantum factoring or global algorithm and so on. The last one, once we have a clean quantum network, then what can we do? There are many things we can do in quantum communication scenario. Clearly, there's a gap between quantum and classical and communication protocols. And also, I want to refer to this one, the last one. Anders Winter, one day, he told me about this Winter's principle. If there's gap, then arbitrary small, then can be amplified. So it's important to find a gap between quantum and classical and find an application to amplify the gap. And then we can see clearly quantum advantages. And all this result is done by, working with my team, and here is my team. So yeah, that's all, and thanks for your attention.
Right, thank you very much. Before we go for a break, maybe just one quick question from the audience. If not, we could take questions and discussions to the break. Let's thank Professor Junwoo Bae again. And I would like to thank all the speakers for this session one more time. Thank you very much. And I believe now we have a break.
Yeah. After a short break, about 10 minutes, we will proceed with the final session at 4:50.
네, 이거 말고 새로 수정하셨다고 하시거든요.
May I ask your attention, please? The international conference will begin shortly at 4:50. Please take your seats. 이제 곧 마지막 세션이 시작됩니다. 자리에 착석 부탁드립니다. 바깥. 네. Okay. Now we will proceed with the final session, session 6, with Professor Bernd Boxteller. Please welcome him.
Thank you very much. Welcome back to the sixth session of the Yonsei Quantum International Conference. The focus of this session is the ultimate goal, applications of quantum computing. And our first speaker is Professor Shisheng Guan from National Taiwan University. Professor Guan received his PhD degree in physics from the University of Maryland in 1999. He held postdoc positions at the University of Queensland and the University of New South Wales. And since 2005, Professor Guan is a professor in physics at NTU. Since 2023, he is NTU's director of the Center of Quantum Science and Engineering. And Professor Guan is also the director of the IBM Quantum Hub at NTU since 2022. His research comprises multiple disciplines of quantum mechanics and quantum information science. Today, Professor Guan is going to talk about the demonstration of quantum computation of molecular properties on NISQ devices in agreement with real experimental data. Thank you. Please welcome Professor Guan.
I'm going to talk about the demonstration of quantum computing for molecular property. Mainly is harmonic vibration frequency on NISQ device with result agreement with experimental data. All right. So mainly I will talk about the variational quantum eigensolver method. So basically we have variational principle. And then, so that means given the quantum system Hamiltonia, you can prepare any trial state, and then you minimize these Hamiltonia. What you get is always larger than the ground state. So you just choose any wave function you want, and then try to minimize it, and try to see how low you can get. Okay. So the first, for molecular system, and then we have Hamiltonia for electron. So we need to do a mapping from electron to qubit. And since once we have the qubit Hamiltonia, then usually number of molecular orbital you use will determine number of qubit you will use. And then for the real machine, usually we have ansatz. The ansatz means we want to prepare this trial wave function or trial state. So you just construct a unitary. This is a quantum circuit. You can have chemistry inspired or hardware efficient or heuristic ansatz. Then once you prepare the trial wave function, then you just measure it and to get the expectation value. In quantum computer, the expectation value is easy because you just prepare your state and then prepare a circuit. Then you run it and measure it. But for traditional computational chemistry, it's very hard because they need to calculate the wave function and then do the integration to find out the expectation value. But so that's why if you can use this quantum computer to measure the expectation value, is maybe you can get some advantage. So this is much of what I have said. It's just that for this prepare these answers, generally I just show you one of them is a chemistry inspired. There's a chemistry inspired. Generally, people normally use CCSD, and there's a how efficient. Generally, I will use some. In our work here, we use this kind of a circuit, real amplitude. Okay, and then you prepare your Hamiltonian at some atomic separation. Then you do calculate the ground state, and then for another distance, you need to calculate your Hamiltonian again, and then find the ground state. Then you map out this potential energy surface, and then the vibration frequency will be in the equilibrium point where the vibration frequency you can calculate there. Usually you just find maybe 5 points around the minima, and then find out the harmonic oscillation frequency, vibration frequency. So in the early demonstration, for example, IBM in 2017, I put up this paper that calculated small molecule. And then later, because there's noise, and then they demonstrate, okay, if you do the error mitigation, then you can reduce the error and fit into this the curve. The curve usually is because they are using because of noise and the limitation, technical limitation. So usually they will use, and because of traditional computational chemistry community, they use the Gaussian orbital, and they use the minimal set because the technical quantum resource. So they just use this as the initial test. But the problem is, the STO3G, a minimal base set, usually do not yield accurate result compared to experimental data. But so the problem is, okay, so to be comparable with the experimental data, a larger base set must be used. For example, in traditional computational chemistry community, if you want to have a result compared to experimental data, you usually need to use larger bases, so-called CCPVDZ basis, which is much larger than the STO3G. But it's hard because now you limit the number of qubits and the circuit depth. So even for simply H2 molecule, if you want to calculate the result comparable to the real experiment data, you need to use 20 qubits. And then the circuit depth usually is 10 to the 4. So that's still beyond the reach of the current NISQ device. So in our work here, we are thinking about, because you use this Gaussian orbital, if we represent a Hamiltonian using a complete basis set, it doesn't matter which basis set you use. But because now you do truncation, you only use finite number of orbital. So that means the choice of the orbital will determine the quality of your Hamiltonian use. Because now our question is, we want to use the minimum number of the orbital and then still have accurate representation of the Hamiltonian. So that's our goal, okay. So the answer would be, we probably should use another basis set rather than Gaussian orbital. Why traditional quantum chemistry community, they want to use Gaussian orbital because classical computer, they need to do integration quite often. Then a Gaussian orbital can give you the analytic result for integration and also differentiation. So they can do it very efficiently on classical computing. But quantum computing, as I say, we don't do integration, we don't do differentiation. We just prepare and measure. So we don't need to use Gaussian orbital. So in other words, we try to represent this Hamiltonian in a small number of orbitals, so smaller matrix. But most of the Hamiltonian, the important term, is already in those small number of bases. Then we can have a very accurate Hamiltonian. Then we can make a good prediction. Only use minimum number of qubits. If your qubit number is reduced, then the circuit shape also reduced. So what kind of basis? We are using this Dobbechi wavelet basis. This Dobbechi wavelet basis has this advantage. You can have this. You can divide this is real space and also basis set wave function approach the basis. So you can define this as fine region. Then you need more grid point, and for this you can use coarse region. You use less function to represent it. Because of the limit of time, I don't have time to go through this method. I just tell you that we are using this wave function, the Dobbechi wavelet molecular orbital. So this orbital can generate from the free software called BigDFT. So we try use this one, and then using the minimal base set for using this Dobbechi wavelet-based molecular orbital for these 3 molecules. Then we only use the minimal base set, so that means the number of orbitals is small. It simulates STO3G, minimal base set. Then we can have accuracy comparable to real experimental data. Okay, but later we are trying to say, okay, we have done this for this small number of molecules. Then we trying to find the row 1 to row 4 for all most of these diatomic molecules. So we consider 43 diatomic molecules. And then we try to use our original method. And then it turned out that the original method has some constraint. Okay, so it does not apply to all of these 43 because other molecule may have some correlation, which is not considered in before. So then we propose a method. It's called. We still use the W wavelet basis set because it already gives us a very good result. And then second, we try to, because we are only using the small number of orbitals to capture the whole, the quality, the high quality of Hamiltonian, but still there are something missing if we only use the Hartree-Fock orbital. So we are using Kong-Xiang orbital, molecular orbital. So that means we introduce exchange functional into our basis set so that using the small number, we can get a more accurate result. The other one is when the molecule become big, then number of qubits also become larger. So we also using this first order independent electron pair approximation criteria to do the active space selection. So in other words, compared to this CCPPD design, they need 20, hydrogen need 20 to 60. In our case, we reduce in only 2 to 12. So we can use 2 to get hydrogen atom accurately compared to experimental result and to other 43 molecules as well. So this is the active space selection criteria. And then this is our the 43 molecule we consider. And here you can show that here we only use 2. Here it has 10. 10 means orbital. The spin orbital multiplied 2, so it's 20. And similarly like this. So we can significantly reduce the number of qubits. This is another method we are using to comparison. Here, we just choose these 3 molecules, and then our method is the number 3 here, which is based or smaller error in this comparison. And this is our method we propose compared to this CCSD method plus the single and double excitation plus triple excitation as a perturbation. So this method is now is the gold standard method in quantum chemistry. What is the gold standard? So that means you cannot do, usually you cannot do better than this. So you can see the root mean square error is comparable to this gold standard method in quantum chemistry. So if you look at this chart, so this one is the experimental value, this is a theoretical value. Then you can see this is our method. This is, okay, maybe this one is more easy to see. This is our approach. This is CCSDT. They are using very large bases, CCPBDZ. Then we only use the, our qubit is less than minimal basis set orbital because we reduce from 60 to 12. So there are, we run this in using this some UCCSD. Then we find that some of the result is not good compared to experimental data. So we think because this is numerical, so we went on to go calculate this using the real amplitude answers. So that means here is number of the layers. So this is the first layer. Number of layer you repeat is 30, and then this 99 is the depth, circuit depth. So we found that within 100 circuit depth 100, most of them can have a result comparable to experimental data. And then the real amplitude outperforms some of the molecule in the UCCSD method. So we are hoping that, okay, if we have, we can have a device who can run 100 circuit depths, then we probably can implement this into the real device. But then later we're thinking about, can we still run this and then reduce the number? Okay, so we pick 3 molecules, H2, LIH, and the PN, and then we test what the circuit depths we need. Here it only needs 4, 12, and the 35. And then 35 is still too deep. So then we are thinking about, and then if we want to calculate the vibration frequency, we need to have several points. So that means we need to calculate several points in order to calculate vibration frequency. So we are using another method to combine the quantum machine learning, unsupervised learning with this VQE. So that means we will input the band length, and also because 35 is still too deep. So what we do is we use this measurement result feed-forward scheme. It's like the neural network. Usually we have this nonlinear activation function in each neuron, but in quantum mechanics, we only have a unitary to prepare this. Unitary evolution is linear. There is no nonlinear function, but quantum mechanics provide another thing because when you do the encoding, you already nonlinear, and also other scheme. So we are proposing, we are using, instead of repeat the circuit many times, we are doing here. We cut it down in here. We do the measurement first, and then feed forward the measure. So the result is this. So we only calculate this, the red point, then we can make out all the potential energy curve. Very. And then for vibration frequency also, we only calculate the 2 point, this 2 point, and then this star is predicted by the machine learning. So then, what we get is this, okay. So for these 3, what we get is the error compared to exact diagonalization compared to experimental data. This is what we get. Okay. And then finally, here is we have also some other work on how to encode the qubit efficiently, and the work here we are in a preparation for publication. All right, thank you.
Thank you very much, Professor Kwon. And an urgent and short question can be taken immediately, if you have one. And for the long questions, please catch Professor Kwon after the session or at the dinner. Let's thank the speaker again. Thank you, Professor Kwon. And our next speaker is Professor Mitsuhisa Sato, who is the Deputy Director at RIKEN. Professor Sato obtained his PhD degree in Information Science from the University of Tokyo in 1990. From 2001, he was a professor at the University of Tsukuba, and he also holds a professorship at Juntendo University. Professor Sato is the Division Director of the Quantum HPC Hybrid Computing Platform Division in the RIKEN Center for Computational Science since 2023. And from 2014 to 2020, he was working as the team leader of the architecture development team in the flagship 2020 project to develop the Japanese flagship supercomputer Fugaku. Professor Sato's research is truly at the intersection of two computing instruments, both of which we can consider computational giants. In today's talk, Professor Sato will introduce his JHPC quantum project for building a quantum HPC hybrid computing platform. Please join me in welcoming Professor Sato.
So thank you for a nice introduction. So it is my pleasure to be here and present our hybrid computing platform project and called JHPC Quantum. So I'm looking forward to collaborate with you to operate and how to use the quantum computer. So currently, I'm a division director of the Quantum HPC Hybrid Computing Platform Division in RIKEN Center for the Computational Science. So before presenting my project, I'd like to introduce myself and our centers. So our center has the mission to operate a national flagship machine of called Fugaku. And the Fugaku is the large-scale, many-core based and massive parallel machine. So, and I was working for the project to build this supercomputer from 10 years ago, and this machine is started in a public service from 3 years ago, and I'm moving to the project and conduct the project to combine this supercomputer with the quantum computer. So we named that project is JHPC Quantum, and the formal title is that very long research and development quantum and supercomputer hybrid computing platform for the exploration of the uncharted computing capabilities. So our project is started November of 2023, and the 1 year and 4 months is already passed. And 5 years project, and the member of our project is RIKEN and the SoftBank. That is the famous mobile phone company in Japan, and also in the University of Tokyo and Osaka universities. And the mission is that, of course, R&D of system software to combine the HPC and the quantum computer. Not just only the development of these software that we are going to build the actual platform, using and installing the actual quantum computer from IBM and Quantinuum with our flagship machine, the Fugaku, and also University of Tokyo and Osaka University's supercomputer. So, of course, the scientific goal is that demonstrate the advantage of quantum HPC hybrid computing, a hybrid application, especially against the existing application and only using the supercomputer. So, and not just scientific goal. So our project is supported by the funding agency, which is managed by the Ministry of the Industry and Trade. So that ministry requests us to making the quantum and HPC hybrid application as the services for next generation of the internet, so post 5G. So the platform we are going to build, currently we are working on this, but so the unique point is that we are going to install the two kind of quantum computer. One is the ion trap from Quantinuum. And this machine is already installed in the Wako campus. And in May, the IBM machine will be installed in the Kobe, in the same building of the Fugaku. So these machines will be connected in a high-speed network. And we also have a small scale, middle scale of the GPU machine. And then we are putting these systems together. We are going to make the quantum HPC hybrid computing platform. And of course, our partner, University of Tokyo and Osaka University has a supercomputer centers. So we have planned to connect our platform to their computers also, supercomputers also. So, and why the quantum HPC hybrid computing platform? So I think I don't have to explain in more detail about this, but I'm coming from the HPC. From HPC point of view, the quantum computer is kind of the accelerator. So the offloading, some useful computation to the quantum computer from the supercomputer. So you can imagine the accelerators as accelerators GPU. So I think the quantum computer is very different from a GPU because current quantum computer needs the special the operation environment like a cryo environment. So in that case, we need the technologies to integrate in a system to system. So quantum computer is also system and the supercomputer system. So we need an integration system to system. So of course, a lot of demand from the quantum computer side. So currently, the number of qubit is the 100. So and even by the IBM. So it's not so much the computing demand for error mitigation or optimization, but in the meantime, the number of qubit is going up to the 1,000. In that case, I believe that we need the more computation in for error mitigation and optimization. So supercomputer can help that. And of course, to design the quantum computer algorithms, I think in a large scale, the quantum simulation is very useful. So let me talk about the hybrid, what kind of application we're looking at. So as many people is pointed out, current quantum computer is a NISQ machine, and VQE or variational algorithm is the main application for NISQ machine. So even that, we are looking at two areas. As a first target, the application area. One is the quantum chemistry. So in this morning, at the beginning of this in a conference, Jay is already talking about our the collaborative project with IBM, the quantum-centric supercomputing. And in this project, we're looking at the quantum chemistry. So, and quantum simulation is the very the expected and the promising application area for the current quantum computer. So now the number of qubits is more than 100. So I think it is somewhat enough to simulate in a certain scale of quantum system. But current NISQ machine has many problems. One is the noise, and another is the very short time for the decoherence. So, as a result, it is difficult to execute in real the application in a current quantum computer. So, and recently is IBM and Jay there, and the declared the world using the word of the quantum utilities, how much useful for how to use in the current quantum computer. So we are very supportive for this concept, and it is important to demonstrate how much useful the current the quantum computer. So IBM and Riken wrote these papers to demonstrate the effect the quantum utilities. So in this application, we propose a sample-based quantum diagonalization algorithms. That algorithms is using but a lot of the execution by the quantum computer for sampling and collecting the data and diagonalization can be executed in the large-scale computation by the Fukaku. So in the previous papers, calculation, both calculation is done offline. That is the quantum computer science, the supercomputer side. But now we are working on they're putting it together and online and do the iteration to define the solution. And the next area we're looking at is the quantum the machine learning. So I think recently many people is interested in kind of transfer learning, combining it to the kind of deep learning process. And I think in the transfer learning with the classic by the GPU and quantum machine learning is a very interesting application area at this moment. Okay, so and for the system software, at the beginning of our project, we did kind of small the experiment connection between the supercomputer Fukaku and quantum computer, which is made by the Riken. So Riken is Riken Center for the Quantum Computing is made a the superconductive qubit machine called A. So we are going to, we did some experiment by connecting the Fugaku to the quantum computer A. So usually quantum computer, current quantum computer is used within a cloud. So users usually log into the cloud and get a certificate and making some quantum circuit and submit and get a result. So in a upper the flow, we did then a kind of implementation for connection between the Fugaku and this A computer by the technique of remote pressure call. So this experiment is successful, but we found that the many problem. So I would say that this type of the programming by just using the RPC is not enough to be used for hybrid computing. So first problem is we need some coordination between the supercomputer and the quantum computer. So most of quantum computer is managed by in a cloud, and classical counterpart is the single node CPU. So in that case, the classical part is very, very cheap, and against a very expensive the quantum computer. But in case of the supercomputer is also the very expensive computing resources. So, and the bad things is that if you think about the MPI, multi-node program, once this program is running, we cannot stop. And of course, the quantum computer is a very important the computing resources. So we need some scheduling or the coordination to be used for these computing resources to be used more efficiently. So we need something. And another small problem is that programming environment. So the Qiskit is a very, very major the programming environment for the quantum computer, but it's based on a Python framework. So Python is a very, very, very good, very useful language, but in a context of the HPC, it's not so easy to use. So usually the HPC application is written by an MPI, the C and C++, even in Fortran, very old language. And we need a we need a programming environment combined to the HPC program to the computer programming. So we offer two level the programming model for the HPC and the quantum application. Upper level is the workflow. So and workflow is that controlling the multiple the independent program by the workflow tools. So you can see it can be the classical program. This can be the in a quantum program. This flow can be controlled by the workflow tools. So and in this case, the program, the hybrid application is composed by independent program of HPC and a quantum program. Then there is but some application need to be more tightly integrated. So and in that case, we provide a more efficient the interface by remote pressure call to execute the quantum circuit within the program. In that case, result can be managed by during the HPC application is running. So of course, we are going to provide a Qiskit environment. So this is mainly for the development. But usually, HPC application, the supercomputer is managed by the job schedulers. So users usually submit the job by the QSub, the job scheduler command. And we are providing a workflow and also an HPC programming framework. Okay. So, and let me talk about our system design policies. So, first priority is that support the quantum HPC hybrid program by making the quantum program and HPC application more efficiently. So system should be enables the efficient use of the HPC and the quantum as well as the quantum computer. And next one is that we want to manage by our own the users. So and here. So and also we are going to provide a more HPC oriented programming environment based on C and C++, as well as the Qiskit environment. So this is an overview of our the design. So here the supercomputer, and this is just cloud and a single server environment. And this is controlled by the workflow. And we are going to make another schedules by our own. And this schedule is the important element of in our system because two things. One is the authentication, and this is important for users management by our own. And another is the priority management from HPC. So this scheduler is control the priorities for each request from the supercomputer and the single node. And then this scheduler enables the execute high priorities request from the HPC. So, and we also support in a multiple the supercomputer. In that case, we need some kind of negotiation between the supercomputer to share in one the quantum computer. So we are now implementing in a kind of a coordination, the middleware to coordinate the supercomputer in different sites. Okay. Let me finish in presenting schedules. So this year is a very, very important and exciting year. So, and as I said in the beginning, the quantum computer is already installed. And from the February, last month, that's quantum computer is available. In May, IBM machine is installed in Kobe. And this year, we are going to start in a test operation. And from year of 2026, we are going to shift more in the operation, this system. And we are going to provide in this platform for the application users to demonstrate in effectiveness or the quantum utilities by their application. So, and we started in a test users program to invite external users who are interested in using our the quantum HPC hybrid computing platform. So if you are interested in our program, please contact me. And I think external collaboration, especially the Yonsei University, is very, very welcome in the future. Thank you very much.
Thank you very much, Professor Sato. And we have time for one urgent and short question. If I may take the opportunity, you said you used 6,400 nodes of Fugaku with the quantum computer. So there's some headroom, right? You have 150,000 nodes. So,
of course, but I think so most of users using in 1,000 nodes or something, and we have a large number of the nodes, but these computing resources will be shared by the many users.
Okay.
No.
So for scalability, if the quantum computer grows, it would not be a problem in the foreseeable future. Like if the quantum computer has twice the number of qubits, then the supercomputer will be able to accommodate.
I don't. I have no idea, but so you know, the next. So the Fugaku project is finished, and now in Fugaku is operated, and next project is started, and new machine will come in 2028 or 2029. So at that time, the computing capability will be in 10 times or 10 times more.
Okay, it's already scaling here. Thank you very much. Let's thank the speaker again. Thank you. And our next speaker, the last speaker of this session, will be Professor Chong-Ho Bang, who is a professor at the Institute of Convergence Research and Education in Advanced Technology here at Yonsei University. He joined quite recently. From 2022 to 2024, Professor Bang was the director of the Quantum Computing Lab at the Electronics and Telecommunications Research Institute, and he was a research fellow at KAIST at the School of Computational Sciences from 2017 to 2021. In today's talk, Professor Bang will discuss the role of quantum computing in shaping post-quantum cryptography. Please join me in welcoming Professor Bang. Thank you.
Thank you for having me, and I'd like to give my special thanks to you all as a member of the Yonsei University. In this talk, I'd like to discuss about post-quantum cryptography and the role of the quantum computation. Actually, several years ago, my second boy showed this picture, and I asked, "What's that?" My second boy said, "This is universe strongest dragon grasshopper." So I asked, what does it mean? Strongest in the universe, and what's the dragon grasshopper? So he said that this is a dragon grasshopper, not the dragon, not the grasshopper. Yeah, and I believe that this is strongest in the universe. Yeah. Okay. So I will show this later again. Okay. Usually I start with in this usual talk. I always start with this statement. Always space theory defines or limits the ability of the information processing. The quantum information science is aiming at developing the faster, safer, and more precise information processing by changing the base theory from the classical to quantum theory. So everyone knows we use qubits which can be superposed and entangled. And there are several candidate physical platforms to realize this qubit system and eventually to build a quantum computer. Actually, the best and simple way to explain why the quantum computer is powerful is quantum parallelism. For example, in the classical computation, we always should identify the input and output one by one. But in the case of the quantum computing, we can use the superposition of the data, and we can process this superposed state at once. But actually, this is not 100% true, because if we should extract a real solution from this superposed state, we should perform the measurement, and then we can get one of them with a certain probability. So we should employ some efficient incorporating operations to improve the solution probability up to unity. Actually, that's the quantum algorithm. Then what's the algorithm? Actually, algorithm is a kind of sequential set of comments for solving a problem. So the algorithm is a real-world terminology, but the algorithm become very important, especially in computer science. It's because the computer can express these states by using a simple 0 or 1 signals, and also the possible to express this command operation with a fundamental set of logical gates. Here, I'd like to inform that the algorithms is not unique. So sometimes we meet the good algorithm, but sometimes we meet the poor algorithm. So the performance analysis is very important. For example, for the equivalent circuit, two circuits, we can directly see this looks better because it's simple with a few gates, and we can imagine that this circuit can generate the output very quickly because the gates, number of gates are small. But in the case of describing the problem hardness, we usually use the ratio or the rate of the increase in the number of gates to the increase in the problem size. For example, the increasing rate is exponential, then we say that this problem is difficult or intractable. But the increasing rate is polynomial, then we say that this problem is easy and tractable. So this is a computational complexity theory. So when we say the quantum computer is powerful, it means that we can solve a problem within the polynomial increase or the polynomial complexity, whereas there's no such a kind of algorithm in the classical computation. The dramatic example is factorization. Everyone knows that factorization can be solved with the polynomial time, whereas there's no such a kind of algorithm in the classical computation. Actually, the advent of this Schwartz algorithm, factorization algorithms, boosted the development of the quantum computing algorithms and other fields. And we also have the very famous quantum algorithm called the data search, which exhibit scale to speed up. And another important quantum algorithm is quantum linear algorithm, often called the HHL, named after these inventors, the Harrow, Hassizm, and L.O.V.E. And this algorithm exhibits the exponential speed up compared to the classical diagonalization method. And this algorithm is special because this algorithm opens a new era and new phase of the quantum machine learning as a kernel of the quantum support vector machine. Okay, then the celebrated quantum algorithms can be a threat to any crypto system, right? So we make this one solution. The first solution is use the quantum, which means that we can create a secure communication scheme and secure protocol by using the quantum principle. So they established very famous subfield like quantum secure communication and quantum key distributions and so on. Okay. Then second solution is to develop the crypto system based on much harder problem, even for the quantum computer. This is a post-quantum cryptography. Okay. Usually, cryptology consists of the two subfields, cryptography and cryptanalysis. Actually, PQC is quite closely related to the cryptanalysis because one of the main purposes of the PQC is to find a hard problem against the quantum computation. Okay, so there are some several candidate problems like this, but as I know, this four case can be solved for under some conditions within polynomial time. And even this isogenic-based problem can be solved, as I know, even with the classical computer by your notebook. Recently proved, as I know. So nowadays, the strong candidate is a lattice-based problem, like shortest vector problem, SVP, or closest vector problem, CVP. But still, we don't know the exact hardness of this problem. Okay, I said one of the main purposes of the PQC is to investigate whether a given problem is hard or not against the quantum computation. So there is a very useful formalism called the hidden subgroup formalism. Okay, for example, let's consider factorization. This hidden subgroup is the natural number set. And we know that this factorization can have the polynomial solution in the quantum computation. Then for a given problem, suppose that you find its a hidden subgroup is the natural number. Then it has been proved that for that problem, we can always find the quantum algorithm to solve that problem within the polynomial time. So what we should do for a given problem, what we should do is to find the hidden subgroup. Then we can evaluate its hardness by using the established table. Okay, it's very useful. So mathematicians is great. Yeah, so in the case of the SVP problem, we know that it's classified as a sub-exponential. But for a specific case, for example, in the ideal lattice, the SVP can be solved within the polynomial time. But in the worst case, still the SVP is a hard problem, exhibiting the sub-exponential complexity. Yeah, so the L.W.E, the learning with errors problem, L.W.E problem is one example of this the worst case SVP problem. Actually, this problem is very easy. Let's consider this linear function. Then the task is to find this, identify this function, namely finding this secret vector S for the given samples. We know that the linear problem can be solved easily which means that we can solve this problem with only polynomial scale of the polynomial size of the samples. But here, if we assume the noise in this output, then this problem becomes intractable. And we call this problem the learning with error problem. So this problem can be considered as a strong candidate for the Pickish crypto system. And recently, this problem it has been shown that this problem is as hard to solve as the several worst-case SVP problem. And the best classical algorithm exhibit this sub-exponential. Then really, is it impossible to solve this problem with quantum? Actually, several years ago, the two papers have been published. In these papers, the Cross and the Grillo, very clearly proved that this L.W. problem can be solved within the polynomial time. Okay? But these two papers also have some caveat. Actually, hint is here in the title. Actually, in the title, exactly mean that learning with error problem can be easy. Can be easy, yeah, when we can use this largely superposed quantum sample. Yeah. So very important thing is the data, actually data, the sample. So this, it means that this, the input sample consists of the very largely superposed classical data. So it's quite difficult to make this kind of, to prepare this kind of the state. Actually, we usually call this problem the QRAM problem. The QRAM is a quantum random access memory. And the second caveat is we should employ very heavy quantum operation like this. The quantum Fourier transform, like this. So several years ago, we considered some simple idea called known as the divide and conquer strategy, which is to divide the system into several fractions and apply the algorithm to the small size system. And here we proved that this strategy can be applied to the L.W. problem, and we can enjoy the exponential speedup even with the small size of the superposition compared to the original Grillo's case. So we published paper. And also after that, we also studied about the overall cost in terms of the FTQ, fault-tolerant quantum computation. Here we consider the overall cost. Here we employ the TDEPS. The reason why we casted the TDEPS is in the first fault-tolerant quantum computation, the T gate is the most expensive gate. So we usually we usually employ this TDEPS as the cost measure to evaluate this implementing circuit in the logical level. Okay, anyway, we investigated the overall cost of this the L.W. algorithm, and we proved that even in this case we can reduce this overall cost down to the polynomial scale. Okay, and also we published the paper. Okay, and so many people asked me, so can they actually attack me? Not the problem. can they break it or not? So I always answer, this question is wrong. Actually, this kind of the discussion always make a meaningless debate. So my answer is I'd like to emphasize that the quantum algorithm researchers should design and develop the quantum algorithm to attack this hard problem. And then the crypto people can use this result to enhance or develop the post-quantum cryptography system. So, and proper interplay between these two, attack and defense, can make the real, the desirable crypto system. Otherwise, there is no quantum algorithm, no crypto analysis, then the PQC meet like this situation. The dragon, blah, blah. Yeah. Which is created by just a belief, not a science. Okay, so summarizing, I'd like to emphasize more. So firstly, there is an overestimate vision about the quantum computer. For example, the quantum computer can solve everything very strong, but this is not true. And also, there is some kind of deterministic claims about the PQC. For example, the quantum computer can never break the PQC. This is not also true. Okay. So I think there is a need for interactive research between these two fields, and we should discuss always. Okay, thank you.
Thank you very much, Professor Bang. And if you have a question, a short question, then we can take it. Or otherwise, after the session, let's thank the speaker again. Thank you very much. This is also the end of the session. And with this, I want to thank our speakers once again for their enlightening talks, and you, the audience, for your interest. And with this, I hand over to Professor Jae-Won Kim, who will deliver the concluding remarks of the Yonsei Quantum International Conference. Thank you.
Thank you. So it was a great week, and we enjoyed it all. And about 10 years ago, if we talk about the quantum computing or quantum communication or quantum sensing, imaging, and metrology, and then there were many negative opinions on that. And the question was, can it be done? But nowadays, the question shifted its focus on not whether it can be done. Now, when can it be done? That is the question. And it needs a lot of effort from not only established generation, but also the young generation. And we need a collective effort. And this reminds me of some heroes' challenge on the very difficult problems, like Columbus. I always think of Columbus. And when the physics provided a new idea that the Earth is round, then the Columbus may not have a very concrete idea of a physics, whether it's really round or not. He may not be able to prove it, but he believed it. And even though he's an Italian, he tried to persuade many kings and queens all over Europe. And then he found a queen in Spain and got the investment. And then he finally went westward to find a new continent. And So now we have definitely know what quantum physics tells us. So now we have to work on this thing. And the last 2 days, the symposium provided us many very wide spectrum of ideas and very different depth of ideas. And so we need to find some application of that, and also we need to train our young generation how to think about the problems, and eventually this will help us, humanity, in the end. So we are going into this direction, and I would like to thank you, all of you, for collaboration and also for the future plans. Thank you so much.
The Yonsei Quantum Week 2025 International Conference has now concluded. Thanks to your interest, the Yonsei Quantum Week 2025 International Conference has successfully come to a rich and fulfilling conclusion. Thank you for participating in the Yonsei Quantum Week 2025 International Conference. Wishing you a safe journey home. And additionally, there will be a photo session shortly. First, we will take photos of the speakers and chairs, followed by a group photo of all participants. Please wait a moment. Speakers and chairs, please come up to the stage.